A very good morning to our distinguished guests, speakers, participants, and dear students. It is my pleasure to welcome you to the second day of the first International Conference on Advanced Materials for Sustainable Innovation 2024, organized by the School of Engineering and Technology, Vivekananda Institute of Professional Studies, Technical Campus. Yesterday was an inspiring start, and we are thrilled to continue the journey today as we explore further into the groundbreaking research and innovation that is shaping the future of sustainable materials. We are privileged to start today's session with the keynote talk titled Past, Present, and Future of Magnificent Magnesium for Engineering and Biomedical Applications, presented by Professor Manoj Gupta, who's joining us online today. Professor Manoj Gupta is a renowned materials scientist who has previously led the materials division at the National University of Singapore. Professor Gupta has earned his PhD from University of California and conducted his postdoctoral research from the University of Alberta. Professor Gupta's pioneering work includes the development of disintegrated melt disposition technique, the energy-efficient hybrid microwave sintering method, and the turning-induced deformation technique. Professor Gupta's contributions have earned him multiple awards and extensive recognition with over 695 peer-reviewed papers, 2 US patents, and 8 co-authored books. Professor Gupta, we are privileged to have you with us today, sir. Please join me in welcoming Professor Manoj Gupta as he begins his talk in a few moments from now. Sir, you can begin.
So many thanks for the introduction and greetings from Singapore. I have a special relationship with Delhi. I'm born and brought up in Delhi, so I understand Delhi and Delhi culture very well. So my today's talk is going to focus on a very fascinating and magnificent magnesium, which is now being targeted for both engineering and biomedical application. Now, this is just like one of my signature talk because this material has immense importance for the benefit of the whole planet, and you will see that how essentially the focus is on magnesium, and magnesium practically has a history of almost 100 years now, and its first glorified use was in the Second World War and around that decade. When you see the image on the left hand side, bottom left hand side, you see that a number of ladies working in the factories that was addressing the products from magnesium that included like tracer bullets, bombs, and lightweight equipment. To note here is a lightweight equipment because at that time there was a disruption in the fuel supply, and hence people understood the importance of lightweighting the engineering structure. And apparently in 1947, the year of our freedom from British rule, we have seen the magnesium coming in the aerospace sector. In 1950, you see the famous Beetle car on which many movies are made. About 20 kg of magnesium was used. So apparently, why the use of magnesium is inevitable? Because it is very important for the planet Earth. It's very important for the plants, animals, and humans. Now, let's start with the happy planet Earth. Are you able to see my slides moving? All right, so you've already heard me about why the magnesium is important. So it is important for uh, practically many aspects of the planet. And let's see the start from the planet Earth here. Are you able to see the moving slides? Hello?
Yes, sir.
Okay. So the main issue that we are facing now, as all of you must be aware, is the global warming. Now, what are the impacts of the global warming? For example, you see that in Chennai, there was flash floods in 2015. The same city have the drought in 2019 and floods again in 2021. And this cycle is repeating much more often than it used to in the past. We have seen in January 2016, for example, forest fire in Alberta zone where the temperature was minus 10 degrees centigrade and the reason was dry air. We have seen many countries in Europe, for example, France is living at 45 degrees C in 2019, and these countries never used to see the temperature beyond 30 degrees centigrade. So these are all some of the impacts of the global warming. Another evidence that you see here in this slide is a big iceberg floating in a neighboring town in Canada. And by look at the people, you can imagine the size of this iceberg. That's an indicator that the Arctic ice is melting, and that is melting because of the global warming. As a result of that, the food habits of the animals are changing, and it will lead to the change in the food habits of the humans also because of various factors that we are facing in a much more increasing way. In this picture, you see a polar bear is hunting on reindeer, which never used to be the case. The polar bear used to go to the sea and get the food. Now, as a result of this global warming, a Paris Agreement was made in 2015, and the goal was to limit the temperature increase to 1.5 degrees C with reference to the temperature in year 1880. In 2023, we have already reached 1.36 degrees centigrade, which is very marginally lower than 1.5 degrees C. And as per the research done by Professor Jason, he says that if we reach 2 degrees beyond 1880 temperature, then we are going to see a new and irreversible state in the climate system. That means no matter what we do, we'll not be able to reverse it. And that can be very catastrophic. So apparently at that time they made some calculation and say that can we like reduce 2 billion tons of CO2 emission by 2025. So in that respect, COVID-19 came as a blessing in disguise. Not that we want to see something like COVID in our lifetime again, but because of the COVID and freezing of all the transportation sector, we were able to save on 2.3 billion tons. Having said that, last 2 years, especially the last 18 months, have been the warmest in the human history because all the industry, all the transportation sector have come back with a vengeance, and we are emitting much more carbon dioxide than we used to do before. So the reason for global warming is CO2 emission or greenhouse gas emission. There are many factors which governs the emission that includes electricity sector, transportation sector, and the industry sector. Electricity sectors, yes, we are making forays into tapping on to the nuclear energy, wind energy, water energy, and so on and so forth. The progress is being made. Industry sector, government is giving a lot of incentive to cut down on the fuel consumption, use cleaner fuels, use the desulfurization facilities, and so on and so forth. Transportation sector, which is very close to the heart of material scientists and mechanical engineer, and now even the electrical engineer, is one of the main contributor of CO2 emission. Now, magnesium is one of the lightest metallic element that can be used in structural application. So if we make the vehicle light, for example, your 1 liter of petrol can give you 25 kilometer and maybe beyond. So basically, you reduce the weight of the vehicle, you reduce the CO2 emission, and you do your part in mitigating the global warming. And that is where magnesium comes in. Now, it's not the automobile sector or the cars I'm talking about. I'm talking about cars, bus, or aerospace sector, space sector, sports sector, defense sector, maritime sector, and the rail sector. So it's a very big area, and this just the replacement of aluminum by magnesium can make a 33% difference in reduction of the weight on component level. Now, why this is important? Because many of you may not know that where we are at this point of time, we have already entered the sixth mass extinction event. The mass extinction event means you lose 70 to 95% of plants, animals, or microorganism species. The first five were created by nature, and the last one we have seen the dinosaurs disappear. Sixth one is created by us because of the wrong choice of technology and the materials. Now, as a result of this reason, especially in the last century, we have seen that CO2 emissions is highest in 800,000 years. Global warming is happening. Arctic Ocean is going to be ice free by 2030. Sea level is rising by about 3.4 millimeter per year. And apparently, the extreme events like droughts, forest fires, floods, and tropical storms are increasing. The frequency is increasing, their duration is increasing. And on the graph on the bottom right hand side, you will see how much the floods and storms are increasing with respect to the say 1960, which is somewhere here. It is an exponential rise. Droughts are also showing their face. So apparently, because of all this thing, the doomsday clock, which predict the uh, doomsday for humans and all the living organism, has been just 90 seconds to midnight. In 2018, it was at 2 minutes. Now 30 seconds, it has moved forward. And this doomsday clock movement is based on the proliferation of nuclear weapon, climate change, and new technologies. So you see that how the climate change and new technologies are important for us to take control of. And looking at the COVID, the proliferation of biological weapon can also create an havoc. So maybe that should be another factor. Let's go on the spiritual side of that. One of the oldest culture, Mayan culture, predicted the uh, end of the world by 21st of December 2012. Nothing really happened, but that was a time when uh, all these scientists were coming together, understanding the uh, issues with the global warming. Now let's try to look at the Hindu philosophy, and if you look at this table, second last row, you will see the end of Kali Yuga is 2025. So now the issue is that if we don't take a uh, proactive approach, then these two philosophies, 2012 to 2025, they have given us a window to act. If we don't act, then we are going to have problem, and this magnitude of the problem will increase. Now, if you look at this slide, for example, the eco anxiety is surfacing in many people all around the world. And the picture on the top very clearly summarizes how the lightning, rains, forest fires, droughts are going to increase the lot of issues, lot of undesirable issues for us. The books are being written to stem down the eco anxiety in a fair amount of population. People are aware of it, especially the young generation. And I see a lot of people in the audience who are students, and you have to take it to the next level to understand, to say no to any material that is toxic, to say no to any technology that is not a green technology. And if you can do that, you can make a change. The life will not be only better for you, but your kids when you get married. Now let's try to see the magnesium in the context of plants. The work done by Australian researchers have shown that anything which goes in the soil may end up in the plant. What you see in the fluorescent images here is the absorption of manganese and the gold in the plant because the soil was rich in that, or you can say contaminated in that. So not only these elements but aluminum also. If you look at the image on the left side, you see the plant on the right hand side is showing the stunted growth of the root. Stunted growth of the root means stunted growth of the plant as well. So now you can be vegetarian, you can be eating a lot of greens, but if your crops are grown on the contaminated soil, all this contamination is in the plant. No matter how you wash it, is not going to go out. So all this toxicity will end up on your dinner plate, which will cause a lot of health issues. If magnesium goes in there, magnesium is a nutritional element for practically all living organisms. And you see the plant on the right hand side is much longer roots, which is an indicator that this plant is going to be very healthy. Let's look into the context of humans and animals. The dog drinking contaminated water turning blue, the person who is intentionally contaminated, fictional character Hulk in the Avengers movie turned green. These are just one real example, one hypothetical example, but this can happen because it can lead to the gene mutation in the long term. And if you look at the image on the right hand side, you will see that if the toxicity goes into you, whether it's by air, by water, or by soil, it's going to lead to a lot of issues like neurological problem, cardiovascular problem, gastric problems, cancers, and so on and so forth. So we want to avoid anything that is toxic. Now, a relation of magnesium and human health, it is involved in 300 chemical reactions in the body. It's important for the muscular system, nervous system, cardiovascular system, immunity system. And if you have trouble sleeping, go to the pharmacy, buy a tablet of magnesium and keep taking that. It's available in the vegetables, grain, beans, nuts, and fish. And don't be surprised that magnesium ion is the fourth most abundant cation in the human body and it is stored in the bones. So osteoporosis is not only a function of calcium but also magnesium. Tinnitus is a hearing issues when people hear some kind of sound when there's no sound, and 15% of U.S. population suffers from tinnitus. Here, magnesium can work as a medicine. You take it with vitamin A, C, and E, and it will relieve the conditions and symptoms of tinnitus. Another issue that our generation now is facing is electromagnetic smog or electromagnetic pollution. Now, all of us have a handphone, we have laptops, we have refrigerator, we have TVs, food mixers, and many electrical gadgets in our home. The common thing in these electronic gadgets, even the microwaves, is that they emit electromagnetic waves, also known as electromagnetic pollution, which is the fifth largest pollution after noise, water, air, and solid waste pollution. When you're in the proximity of these devices and they're working, they emit electromagnetic waves absorbed by the body. Body does not know what to do with that, and it affects the metabolism and hormone production. When that happens, then it leads to something undesirable in the body, and that is where the World Health Organization has classified that as group 2B, possibly carcinogenic, means cancerous. No boundaries. This pollution has no boundaries. Everyone in the world have all these electronic gadgets. So we worked on magnesium and compared with aluminum, and we found that the radio wave shielding and microwave shielding of magnesium is similar or better than aluminum, which is commonly used for electromagnetic shielding. So I want to replace now aluminum by magnesium. The reason, I make my phone lighter, I make my laptop lighter. I replace aluminum, which is a neurotoxic element, by magnesium, which is a nutritional element. So it's a win-win situation for me to use magnesium. And that is where the industry is trying to move. Now let's try to look at magnesium in the periodic table. It's in the group 2A, alkaline earth metal, which has a low melting point at 650 degrees C, density one of the lowest among the metallic material, wonderful specific strength, wonderful damping, wonderful electromagnetic shielding, acceptable ductility, acceptable modulus, and cost which is slightly higher than that of aluminum. Negative, it corrodes. But remember, all metal corrode. So if you have to use magnesium, ensure it is corrosion resistance, or you use the techniques for corrosion resistance like coating. Now let's compare magnesium with the workhorses of metal like aluminum base alloys, titanium base alloy, and steels. And if you look at the graph on your left hand side, you see that magnesium has the lowest density, it has one of the lowest melting point, it has one of the similar specific modulus and specific strength next to titanium, but titanium comes at 5 times the cost. Now, if you look at the graph, for example, on your right hand side, you see the y-axis is strength, x-axis is density, and the strength spectrum of magnesium is half that of aluminum. It overlaps with titanium, steel, and nickel. So that means we can replace aluminum, titanium, steel, and nickel with magnesium when the design is a strength-based design. And to expand the use of magnesium, the spectrum of the strength has to increase so that it can be used in more and more application. Sustainability is a big thing which everyone talks about. So are we short of magnesium? The answer is no. It's the sixth most abundant element in earth crust. It is the third most dissolved mineral in the seawater. And remember, I told you 4% in human body. So it is everywhere, living and non-living. In the earth, it is 12 times more than that of aluminum. So that means if aluminum lasts for 100 years, this will last for 1200 years based on the existing rate of consumption. Let's try to look into the universe. Magnesium is even more available than iron. And that's why I say that magnesium is a God's own element. So if we are planning to colonize Moon or Mars in the future or any other moon of Saturn or Jupiter, basically we can always take the magnesium technology with us and you can expect to find magnesium there. And now here is the recent news actually when the NASA tried to get some of the sample from an asteroid. The name is Bennu, and they find very interesting magnesium sodium phosphate. And they indicated that magnesium serves as a component of biochemistry of life, magnesium, sodium, and phosphorus. So magnesium is everywhere. So in the image on your right hand side, all these shiny crystals are magnesium-based crystals. Now, people used to say, or they were in the impression that magnesium can catch fire because when we were in the school, we used to burn magnesium ribbons and magnesium powder. But that is not true when you use the magnesium in the bulk form. And I'll cite you certain example to show that how the magnesium was used, not only at ambient temperature, but also at the elevated temperature. So this image you have seen in my cover slide, the Beetle car using 20 kg of magnesium. And the image on the right hand side, you see magnesium is used in the engine component. Now the General Motor, which used to make our Ambassador car, have introduced magnesium in the boot area way back in 2012. Slogan is simple: 75% lighter than steel, 33% lighter than aluminum, and the whole world is going to carbon zero, and carbon tax is coming in. Let's go to another brand name, Bosch. They replaced the roof way back in 2019 by magnesium. They compare it with CFRP, carbon fiber reinforced plastic and aluminum, and they told through the advertisement that magnesium is the thinnest, strongest, and lightest material. And just by changing the sheet on the roof, they were able to save 10 kg of the vehicle weight. South Korea has done a wonderful job creating a roadmap of using magnesium way back in 2016. And now you can see the magnesium wheels are coming in. Maruti Suzuki is using magnesium steering wheel for many, many years already. It's coming in the lamp casing and all these things. So now if the cars are getting lighter, you can expect that magnesium is coming more and more. Let's look at the aerospace sector. Convair aircraft, 1947, the image on my cover slide, used magnesium. Convair B-36 Peacemaker with 8.6 tons of magnesium, and we are talking of 50s to 60s roughly. Helicopters, 115 kgs of magnesium. Lockheed F-80C, fully made of magnesium. Russian bomber, 1.5 tons of magnesium. So as a result of that, there's a lot of pressure on FAA to lift the ban on using magnesium in the commercial sector. And they agreed to that in 2015. And the logic given to them was very simple, that I save 360 kg in a narrow body plane and about 4.2 tons for a 700-seater Airbus A380. I can reduce my fuel consumption. I can go a bit more green. So they say, fine, but ensure you do the testing for flammability, which is a reasonable request. Now let's try to look at the maritime. What you see here, the amphibious vehicles, or the vehicles that are capable of operating both in land and sea, and they have to be lightweight. And the reason is simple, because if you're lightweight, you can run longer distance, you can be in the war zone for a longer time. Cruise ships, magnesium-based engines are commonly used. Armored vehicles like it can be 6-ton vehicle or 25-ton vehicle. They can carry medium caliber gun system. They have to be light so that once again you can be in the war zone for a longer time. You don't have to come back for refueling. And based on the calculation, you save on 17% of the weight of the vehicle if you use magnesium judiciously. Now, one of the lightest 15.6-inch laptop, which got the 2016 IF Design Award, was made of magnesium. So, ergonomic advantage by using magnesium and structural components in electronic sector people are planning to use in the TV frames, camera frames, robotics where steel is used. Now imagine the energy required to use or energy required to move these parts in a robot. Much more energy because steel is very heavy, 75% heavier, and the response time accordingly will be slow. So if you use magnesium, you reduce by 75% weight, you reduce the energy consumption, and you can increase the response time. 10 years back, Japanese were already trying a system level testing in which all the sleeper berth has to be replaced by magnesium. So you can expect that their high speed train will already have magnesium sleeper berth. Now let's try to touch a bit of the research part, and I'm going to introduce the two techniques which was indicated by the MC in the beginning. And first of that is the uh, disintegrated metal deposition technique. Is the combination of casting and the spray deposition technique. Here we take the material in a crucible, graphite crucible. We use the resistance heating to heat it. We stir the material, which can be a monolithic material or a composite material. We bottom pour it, and once we are pouring, we hit with the argon gas jets so that it is split into droplets, and then we collect it at the base of the chamber. And what you see on the right hand side is the typical facility that we have in the lab, working very well for last 30 years now. And the, these are the ingots you can get, you can machine to billet and the rods. And the second technique that we developed somewhere in 2005 is the powder technique, where we use a microwave for sintering. So in a typical powder technique, we take the metal powder, or if you're making a composite, you can add reinforcement, you blend it, compact it, sinter it. Most of the researchers use a tube furnace to sinter it, and we modified the microwave based on some of the initial work in 80s and 90s in Penn State. And what we did was to create this inner, I will say, reactor chamber here. So where we do is that we take an outer crucible here, a inner crucible here. In between, we put silicon carbide as a susceptor. We took the metallic ingot, pretty good in size, 35 in diameter and about 40 in length, and we just covered with the insulation. Now, when we sinter the material like magnesium, we have tried for magnesium, aluminum, solder materials, and so on and so forth. So for magnesium, we are able to sinter in 14 minutes, which is a 90% reduction in heating duration. Temperature 640, I don't have to use inert gas, air is good enough, and the energy consumption is also reduced by more than 90%. So the reduction in heating duration means my productivity increases. Reduction in the energy consumption means my method is green method, I'm using less energy. And the reduction in the heating duration and energy consumption make my product cheaper than my competitors. So that is where sometimes you have to go to the newer technology to make your materials. And here is that when you switch on the microwave, it heats the susceptor and it heats the billet, which also get heated from inside out because it also absorbs microwaves directly. Now, one of the material on which I worked is the magnesium-based nanocomposites. In the nanocomposite, we use the reinforcement at nano length scale. Typically in 80s and 90s and year 2000, most of the research was done on the micron size reinforcement. As you see in the images here, you apply the tensile stresses, the particle can break or debond. Once the breaking and debonding happens, your properties get compromised and you are not able to realize a full fracture strain or ductility and the strength. So we reduce the size to nano-length scale, less than 100 nanometer, and by doing that, we are able to improve the ductility, modulus, dynamic properties, high temperature stability, creep properties, wear properties, fatigue properties, dry and wet corrosion resistance, ignition characteristics, electromagnetic interference, and the power response. So I'll give you only one example. For example, if you look at the row number 2 here among the elements, you see that this alloy shows a strength of 260 megapascal, UCS of about 585, and failure strain of 12.6%. Now, the importance of this value is that these values are greater than a WE43 alloys, which is used in the aerospace application and come with a very high price tag. Then we put about 2% of zinc oxide reinforcement in there, and I increase my strength by another 100 megapascal in the yield stress, another 100 megapascal in UCS, and my fracture strain stays beyond 10%. That means I still have very good formability. It's not brittle. So the importance of these numbers is that now these exceeds that of the mild steel or construction steel like S275 and S355. 75% weight saving here, and a tremendous amount of cost saving if you just want to use the alloy. So these are just one of the example of development of magnesium alloys and using the nanocomposite technology. Another upcoming application of magnesium is not like it was not realized before, but we did not have enough good magnesium-based alloys 100 years back, but people did try even at that time, is the use of magnesium implants in the human body. There are two types of implants in the human body. Permanent implant like hip implant and knee implant, where we want them to stay in the body forever. But then we have implants like bone fracture and all this thing where once the healing is done, you don't want implant there. And many times the patient has to go through a second surgery to remove the implants there. Now what happens if we use magnesium? Magnesium can be absorbed by the body. So we take an alloy, we take a magnesium plate and the screws, we fix the bone. And over the time, the body dissolve the implant, and within 2 years, you'll be free of any metal. You'll be free of any metal. So no second revision surgery as required with steel implants or titanium implant that saves the doctor's cost, that saves the patient trauma. And that is where the industry is moving in now. And we already have magnesium stents in the market. We already have compression screws in the market. Remember, magnesium is a nutritional element. We need 200 to 400 mg, depending on your age, every day to maintain good bodily functions. Now, we created a number of nanocomposites of magnesium with titanium-based reinforcement because titanium is also biocompatible, it's not toxic element. And we compared with the strength of the bone. The maximum strength of the bone is 149 megapascal, and all our strength level were higher than that. Then we also try to look at the compressive properties, and once again the compressive properties were much higher than that of the strength depicted or exhibited or displayed by the bone. And that is not enough because when you put a material in the body, it has to meet two requirements, mechanical requirements and bio requirements. So we have to see how fast it's going to corrode. So we tested these materials in a biological fluid DMEM plus 10% FBS, and we also discussed with doctors. So you need doctors in your team. And they said that any corrosion rate which is less than 0.1 millimeter per year will be suitable as a temporary implant. So we try to do that. Many of the composition fit the criteria. We send this composition to the doctors, now pure medical doctors. And they did the cell viability because the cell has to live on this material. And based on the cell viability, they say that most of the time survivability is more than 75%, indicating that it has zero cytotoxicity based on the international standards. The last use of magnesium is to replace plastic. I don't know how many of you know that plastic is a nuisance. Australian researchers have said that 14 million tons of microplastic, less than 5 mm size, litter the ocean floor. And American researchers have indicated by testing the stools of the people from 10 different countries in 10 different geographical locations with 10 different habits that they have the microplastic in their body. Microplastic, any plastic that is less than 5 mm in dimensions. Now, 9 different plastics were found in the gut of the humans, and they can enter your bloodstream, lymphatic system, liver, and you get them in tap water, soft drinks, salt beer, oceans, flying insects, fishes, and birds. And most of them are dominated by polypropylene and polyethylene terephthalate. And not only if you're like even if you're a vegetarian, the plastic can breach the roots if their size is around 2.5 micron, so you are not safe from the plastic. It can lead to cancer, weakened immunity system, reproductive problem, nervous issues, and hearing loss. So now the plastic have a density of 1.5 gram per cc to about 2.2 gram per cc if you're using in the composite form. So you can compositionally modify plastic by means the magnesium to replace plastic. For example, you put lithium in magnesium and you can make, as you see, this guy is floating, almost floating in the water, while the pure magnesium is sinking there in this container. Now imagine making the boats and the ship with compositionally modified magnesium. It will never sink. It will never sink. And that is where the people are targeting. Secondly, in many defense applications and all these things, plastics are used because of their low density. You can replace all of them by magnesium. So once again, this kind of material can be made by composition modification, as I've shown you the example with lithium, or you can use the hollow reinforcements. Conclusions. Now, there is tremendous scope of magnesium in its pure form, in its alloy form, in the nanocomposite form, or composite form. So, its use is emerging. 2020 to 2030 is when the industry is already coming in and putting in the application. So, window is still open. If we don't act now, we may be a bit late in the race and we may lose a lot economically. Multi-billion dollar market for crap. I will not be surprised if it has reached $1 trillion market. You don't need any special things to make this kind of material. The conventional processing methods are good enough. Whatever you use from aluminum, you can use for magnesium. So no additional infrastructure cost, something which industry looks at. And if you use a nanoparticle, you can increase both strength and ductility, mechanical properties, and biomedical properties. So they have a lot of potential. The only drawback is the industry has to come in so that this method can be scaled up for use. Amorphous and hollow reinforcement are also promising. And once again, the most important is that magnesium can improve the quality of water, soil, and air. And remember, Panchabhutas, 5 elements that makes everything, including us, and the large cosmic order. Out of those 5, we can take care of 3 elements: water, soil, and air. We don't know about fire and Akash, but that is shows the importance of magnesium. So my final remark, magnesium technology has arrived and it's time for industry to adopt for their benefit and benefit of planet living. This is in particular context of the Indian industry because many of the advanced countries like Germany, South Korea, China, they have already being used, they already have a roadmap, they have already put the products outside. So acknowledgement to all my students over the year, and I would like to thank you for your attention. I'm open to the question. You can ask through the chat box or you can ask otherwise.
Thank you, Professor Manoj Gupta, for your insightful presentation. If anybody has a question, the floor is open. You can come up on the dais and ask your question.
Professor Gupta, very good morning. Actually, a very wonderful talk. So I'm Umesh Tiwari from a CSIR lab in Chandigarh. So actually, in our lab also we have a implant manufacturing facility, but their implant are the titanium based. So as you have mentioned in your talk, magnesium can be a good element for the implants, right? So is it like it can be replaced by titanium? Is basically they are the permanent implant, right? Hip implants and the special implant.
Yeah,
So I hope the titanium, it has own benefits, right? And maybe the magnesium is just for the temporary kind of thing, right?
correct.
Thank you.
And I would like to add on to that there are many places where titanium is used even as a temporary implant, like bone fixation and in the oral cavity, which they say is a long word, oral maxillofacial application. Also, these kind of plants are used in the cranial application, that means in the head. But you don't need to use titanium there, and that is where the people are coming in. So they are not targeting permanent implant, as I said. So they are using the titanium and steel where the scope is for temporary implant, where you need this revision surgery to remove it. So in that application you can do it. So I'm also working with a dentist, and they are planning, they found the strength of magnesium can easily match with that of titanium, right? So they are even using in the oral cavities now. So they are doing research in that area. Another company what we are working with, they are using in the cranial fractures. So cranial fracture is not a load bearing area. So where they have a fracture, they put a kind of a strip and they put the titanium nails there. So what happens over the time, especially when you are young and your body is growing, is the bone grows over it. And when the bone grows over it, now your titanium is there in your body for your life. And to avoid that, they are planning to use magnesium now. So if you put magnesium inside there, it's not going to stay there. The body will dissolve it as the healing process goes on. So that is the advantage. So that is the area. And that is where many researchers are working in China, Germany, USA, and some other countries in Europe. So it's a matter of time. One or two products are out already. But what mistake was done by one of these companies, that they put a price tag because they know that they are unique and all this thing. They put a price tag which is more than the cost of titanium alloy or titanium implant. And that is the mistake they did, because for making these material, magnesium is not as expensive as titanium, is 1/5 of the cost. So they should have kept it at an affordable price and still make money out of it. So that's a mistake. But the market is wide open. I'll not be surprised in 1 or 2 years you'll see someone coming in a big way. And FDA in USA has already approved just last year the use of magnesium in the human body. And once the American market has accepted, you assume that, it's just like opening a can of worm. It is going to spread very quickly.
Okay, sir. Thank you, sir. We have another question for you.
Yeah, sure.
Good morning, Professor Gupta.
Good morning.
Myself, Noorzama Khan from IIT Srinagar. So you have delivered such an informative talk. I have a question that you have mentioned 2 processing routes to fabricate the magnesium alloys. So what could be the suitable route for mass production?
The mass production, it depends on two things. It depends principally on the size of your component. Typically, if your size of component is complex and bit bigger, then you go for the casting route. That means the liquid metallurgy route. If your part is symmetrical, smaller, simpler in shape, then powder metallurgy is used. So it all depends on your geometry and the size of your end product. I have seen both casting route and powder metallurgy route as the mass production routes.
All right, thank
Because
you.
it is not easy to compress large parts of the complex shape. So powder metallurgy goes away there actually. So that is where the casting comes in. So I hope I answered your question. Yeah.
Yes, sir. Thank you so much, sir. We will unfortunately not be able to take any more questions since we are running out of time. So on behalf of the institution, I would now like to thank Professor Gupta once again for sharing his invaluable research, and we hope to see you again in the future with us, sir. Thank you so much for being with us here today. Thank you.
Absolutely. It was a medical emergency at the home, so I could not personally come, but yeah, I was looking forward to visit. So definitely, next opportunity I will come.
Yes, sir. We will, we will be very thankful if you can come here in person. Thank you.
Yeah.
Thank you,
Thank
sir.
you. Thank you. Bye, everyone.
Yes.
It is my pleasure to introduce Dr. Noor Zaman Khan, an esteemed scholar in production and materials engineering. Dr. Khan is an assistant professor in the Department of Mechanical Engineering at the National Institute of Technology, NIT, Srinagar, Jammu and Kashmir. Additionally, he serves as an innovation ambassador at the Institute Innovation Council, NIT, Srinagar. Dr. Khan's academic contributions are extensive, with around 60 research articles published in international journals and conferences. He is the author of a book published by CRC Press, has contributed 7 book chapters, and holds 3 patents. Dr. Khan also serves as an associate editor for several international journals. Under his guidance, the NIT Srinagar team secured victory at the Smart India Hackathon 2019. Sir, I request you to join us on the stage, please. Please welcome him with a good round of applause. Over to you, sir.
Thank you very much. Esteemed speaker. Hello? Hello? Yeah, it's okay. Faculty members of NIT Srinagar, faculty members of VIPS, dear students, a very good morning all of you. So myself, Noor Zaman Khan, I'm an assistant professor in the Department of Mechanical Engineering, NIT Srinagar. I'm here to deliver a keynote talk on advancing sustainable development goal, leveraging lightweight magnesium alloys for climate action. Dr. Manoj Gupta, he has delivered a very informative talk on magnesium alloys. So my topic is somewhat closely related to the topic of Professor Manoj Gupta, and he has already discussed about various advantages of magnesium alloys for transportation and industrial applications. So we are already running out of time, so I will try to finish my talk in next 25 minutes. First of all, I will discuss about the NIT Srinagar and some facilities available in NIT Srinagar for 5 to 6 minutes, and then I'll move to the theme of the talk. I'll try to finish the talk by 11:30 a.m. Okay, so I think you can see the beautiful campus of NIT Srinagar, which is established in 1960s, and it is one of the oldest RECs of India. I think it's the 3rd oldest REC of India, and it acquires the status of NIT, which is National Institute of Technology, in 2003. It is situated at the bank of the world famous Dal Lake. So we are having a very nice campus at NIT Srinagar. So I request you all to visit the campus once. And these are some glimpses of NIT Srinagar, of my campus. I'm enjoying the campus for last 6 years. I joined NIT Srinagar in 2018, October 2018. So these are some pictures of the campus of NIT Srinagar. Yeah, another figure, the left side figure I clicked from my quarter actually. So there is NIT Srinagar is a residential campus. We are having on-campus accommodation. So these are some pictures of NIT Srinagar campus. Now, if we talk about the facilities available at NIT Srinagar, so with my team, with Professor Saad Parvez, with the support of Professor Saad Parvez, we have procured this machine from Germany. The company is DMG Mori India Private Limited in 2020 during COVID. So if I'm not wrong, this facility is not available in any NITs of India. It's worth around 5 crores. So what's the benefit of this facility? Generally, if you talk about various applications, various complicated applications, this is an era of the CNC programming. So as Professor Manoj Gupta mentioned, to produce the raw material, to fabricate the magnesium alloy in the form of raw material. So the point is, we need to convert this raw material in the complex and complicated components. So what could be the possible route in order to minimize the energy consumption, in order to improve the productivity? So the route is the CNC machines. Second important application is, if I want to produce the turbine blades, so we cannot produce turbine blade on 5-axis CNC machine. It requires additional 2-axis. So we can produce the turbine blades, we can produce various components for defense applications with the help of 5-axis CNC machine. And the capacity of this machine is, the spindle power is 30 kilowatt and the maximum RPM is 15,000 RPM. So without wasting time, I'll show you a small video and then I'll move to the theme of the talk. How can I play? Yeah. I think 1 more minute is remaining. So I think you must have understood the capabilities of the 5-axis CNC machine. So we can perform even a micro machining for any component by using this machine, and the accuracy of this machine is 6 micrometer. So if you want to produce the micro gears of wristwatch, we can use this type of CNC machines. Now come to the theme of the today's talk, because Professor Manoj Gupta already discussed about the use of magnesium alloy, so I will not focus much on the application. Just to discuss the background of today's talk is, so if you see the left of figure, the earth is split into two halves. One is the green, the thriving portion, another is the dry and the cracked portion. So this is the result of human activities on the health of the planet due to the emissions due to resource overuse. So if you look at various sources of air pollution, starting from the industries, the roads, the agriculture, etc. So we look at the study by the US researcher, and they have claimed around the contribution of the transportation sector is around, it's not clear how much is, 27%. So the contribution of the transportation sector is 27% in air pollution. So due to the emissions like carbon dioxide and methane gas. So what's the impact of these emissions? What's the impact of these greenhouse gas emissions? The impact, the accumulation of these gases will result in the long-term shift in the temperature and the weather condition, which we call as a climate change. So what's the consequence of this? Due to this, the earth is now 1.1 degrees Celsius warmer than the late 19th century, which lead to the melting of the polar ice, which lead to the rising sea levels, etc. So these are the consequences. So what's the solution? How to minimize the emissions in transportation sector? So one possible solution could be the reducing the weight of the vehicle. So all see, if you talk about the people, they generally talk about how we reduce the vehicle, just use the lightweight material. We should utilize lightweight material in some structural applications. But what about the passenger safety? I think you can compare the Swift with the Tata Punch, I guess. So if you talk about the mileage, you get the good mileage in Swift, but if you talk about the 5-star rating, you get in Tata Punch. How to improve the mileage without compromising the passenger safety? So the possible solution could be the use of lightweight material after improving its strength. It means that we should use the lightweight material, but without compromising the strength of the material being used. Let's discuss about the 2030 agenda. United Nations, along with the 193 UN member states, they established the Sustainable Development Goal in 2015, and they want to achieve them by 2030, starting from the no poverty, no hunger, goes to the climate change. So the today's topic is to focus the sustainable goal number 13, which is the climate change. So the possible solution could be the use of lightweight material. What's the advantage of using lightweight material in automobile? It will reduce the fuel consumption, it will enhance the energy efficiency, it will improve the productivity, it will cut it short or reduce the carbon dioxide emissions or greenhouse gas emissions. If we take an example, apart from the theory, if we take the experimental example, a 10% reduction in the overall weight of the passenger vehicle, it can result in saving the fuel up to 20 to 30% without significant changes in the design. So I think you can see, just by reducing the 10% weight of the vehicle, we can reduce the 20 to 30% fuel consumption without significant changes in the design. It means that we can use lightweight material for minimizing the emissions, for minimizing the fuel consumptions, for enhancing the energy efficiency. So again, the same discussion, the magnesium having the lightest density with some possible strength. If you see the rolling force and the gradient force, these all are depend upon the mass of the vehicle. So if you reduce the weight, it will ultimately reduce the rolling resistance and gradient resistance of the vehicle. So if we use, if we compare the magnesium and aluminum cars with the reference car, suppose a reference car having 100% somewhat weight or 100 kg weight. So if we use aluminum by replacing steel or high density alloy, we can reduce the weight till we can come up with the 64% of the weight. So if we use the magnesium alloys, we can further reduce the weight to 50% in future, not highly being used in future, because research is going on magnesium. We can use magnesium for reducing weight, but research are going on how to improve the strength. So here the challenge is for improving the ductility which is required, because see, if we talk about the Indian market, if we talk about us, we generally look on the performance of the vehicle, of course, but we are focused on the aesthetics also. So in order to get the very complicated, very appearing design of the vehicle, we need to have good ductility of the material being used. And if you talk about the magnesium alloys, they are having lightweight material, but they are not having good ductility to form. It means that they are having poor formability along with the poor tensile strength. So the challenge here is, so if we talk about the mechanical properties, if we increase the strength of any metal, it will reduce the ductility. If we increase the ductility of any metal, it will reduce the strength. But if we talk about our requirement, we require this synergy between the strength and the ductility. It means that we need to increase both the strength as well as the ductility. So this is the graph showing the global fuel economy targets and lightweight production by various countries. In 2016, the Europe target was around 125 gram per kilometer carbon dioxide emission, and they have the target to 2025. Why magnesium alloys? So I won't focus much on this slide because Professor Gupta already discussed about the advantages of magnesium. Magnesium having low density, high strength to weight ratio, excellent castability, high recyclability, good thermal conductivity. Now the problem with the magnesium and magnesium alloys is it's very brittle and having low strength. Pure magnesium, I'm talking about pure magnesium, it's very brittle and low strength. If material is brittle, we cannot deform it. It won't deform, it will break. If it's having low strength, we cannot use for automobile because we need to compromise, we don't need to compromise the passenger safety. So what could be the possible solution? Solution could be the alloying. So we can go for alloying various elements, aluminum, zinc, silicon, manganese, other rare earth materials, cerium, yttrium, etc. in order to improve the strength as well as the ductility. This could be one of the possible solutions. Magnesium alloy starting from 1932 till 2022. These are possible applications of magnesium alloys currently being used in various applications. The cast helicopter transmission housing, in various thrust reversal cascade casting of Boeing 737, 747 till 767. So these are some applications of magnesium alloys. Limitation, there are not only the property is the limitation, another limitation is the anisotropy. Any idea about anisotropy? If you talk about anisotropy, it means the material possessing different properties in different direction. It depends on the direction of the application of load. Suppose this is the plate of magnesium alloy. If you are checking the strength in this direction, it will be having different strength. If you are checking strength in this direction, it will give this different strength. So this is anisotropy. So if we are using any material which is anisotropic, it will be very difficult to be used in various industrial applications. So there are two limitations, we have to address two limitations. First of all, we have to improve the mechanical properties, which could be the strength and the ductility. Another, how to cope up with the anisotropy. So I think I no need to discuss, I should not discuss the technical content of material science. This is nothing but the slip system of magnesium alloys. Very brief. If you want to deform any material, there are some slip systems. In magnesium, there are three different planes: basal plane, prismatic plane, and pyramidal plane. So if you want to deform magnesium, the basal plane slip system active at room temperature. But other two slip systems are not active at room temperature. It means that if you are deforming magnesium at room temperature, only one slip system is active, due to which you cannot deform it completely. It will lead to formation of micro cracks. Suppose if you are having the pen made up of magnesium, if you want to bend it, it will lead to the formation of some micro cracks. So the target is how to activate all slip systems. If you want to activate slip system, you have to increase the temperature. It should be more than 200 degree centigrade. Now what's the problem? If we increase the temperature of magnesium above 200 degree centigrade, it will lead to grain growth. And if you have ever heard about Hall-Peck relationship, if the grain size is larger, it will reduce the hardness and strength. Due to grain growth, grain size will increase, it will decrease the mechanical properties. So on the see, now you are increasing, you are activating the slip system. On the other hand, you are reducing the strength. But we require to enhance both the strength, ductility, and deformation. So it will lead to poor strength. If it is a poor strength, there is some word which is critical resolved shear stress. Okay, so ultimately magnesium having poor strength and poor formability even after alloying. So what could be the possible solution? Again, texture. So we can improve the strength, and we can minimize the texture, we can enhance the texture weakening. There are possible solutions which are severe plastic deformation processes. Either you go for multi-axial forging, in this direction hammering, this direction, and this direction, multi-axial forging. If you are performing forging operation in multi-axis, you can achieve severe plastic deformation. Another could be the accumulative back extrusion, equi-channel angular pressing, and the last is the friction stir processing. And my area is friction stir processing. Okay, friction stir processing, it is a solid state processing method. It works on the principle of friction stir welding, invented by Wayne M. Thomas in 1991 in the Welding Institute, Cambridge. You know the beauty of friction stir welding, invented in 1991. Before the invention of friction stir welding in aircraft, in order to join aluminum alloys, they were using rivets, because it is very difficult to join aerospace grade aluminum alloys by fusion and welding, arc welding, gas welding. So if you see, it is very difficult to join these alloys, so that's why they were using rivets, and rivets having their own weight. The target is how to reduce the weight, and if we are using rivets, it carries their own weight. So after 1991, the rivets were replaced by the friction stir welding, and now the Boeing Dreamliner 787, around 70% of welding is being done by friction stir welding process. Now this is friction stir processing, a solid state processing method. It uses a non-consumable tool used for performing the severe plastic deformation. Experimental setup, schematic. Just see the difference in both the figures. Process zone and base material. What's the difference? Process zone and base material. If you can see, the grain size of base material is large. And after friction stir processing, you can see the process zone grain size. It can reduce the grain size starting from even 80 micrometer to 0.9 micrometer. So if we are reducing the grain size, we can increase the strength and the hardness. These are possible application of friction stir processing. Case study. Okay, I'll move. If you see the microstructure, A figure is the base material microstructure, the B and C are the friction stir processed microstructure. You can see the difference in the grain size. If you see this  so you can see the difference in the grain size. A is the base material, the raw material, and B and C are the material after friction stir processing, or you can say after severe plastic deformation. The drastic reduction in the grain size, so we can enhance the strength. Micro hardness, tensile strength, you can see base material tensile strength, and you can see the DP tensile strength. This is the conclusion. So 2030 Agenda for Sustainable Development serves a global framework. Magnesium has the lowest density compared to other structural materials. It retains some reasonable strength after severe plastic deformation. And the key challenge in using the magnesium, how to improve the ductility. So it's all from my side. If you have any question, I think I'm on time.
Thank you, Dr. Noor Zaman Khan, for your inspiring session. Your expertise has greatly enriched our conference. To take this session forward, I request Vidushi ma'am to come to the podium.
As we proceed with our program, we are excited to explore some of the most influential advancements in manufacturing and engineering. Our next speaker is a distinguished figure with over 15 years of experience and exceptional contribution to both academia and industry. I would like to invite Professor Jupiter H.P. Manarung to join us virtually and officially welcome Sir to our conference. Professor Manarung's expertise spans virtual manufacturing, weld fatigue integrity, advanced welding technology, and quality and reliability engineering. He has served as the director of the Smart Manufacturing Research Institute at Mara Technological University, Malaysia, and currently holds the position of adjunct professor at the University of North Sumatra in Indonesia. Professor Manarung's work is distinguished by his innovative approach at solving complex industrial challenges through advanced simulation techniques, pioneering welding technologies, and rigorous quality engineering methods. His research has set new benchmarks in industry, while his insight into the weld fatigue integrity have significantly advanced our understanding of weld design and life extension techniques. His commitment to fostering international collaboration is evident in his role as a trusted partner in bridging the technological and academic landscape of Germany, Malaysia, and Indonesia. Through his strategic leadership, he has facilitated numerous collaboration between universities and industries, driving innovation and business development across these regions. Now, without further ado, I would like to invite Professor Manarung to start his session online on the topic in the importance of technology parameters and material modeling in virtual manufacturing. Let us welcome him with a warm round of applause. Good morning, sir.
Yes, good afternoon here. Yeah, I'm now in Medan in Indonesia. So can I share my, can you hear me, yeah?
Yes, sir, we can hear you.
Okay, so can I share my slide now?
Sure, sir.
So ladies and gentlemen, can you see my slide?
Yes, we can see your slide, sir.
Okay, thank you very much. Okay, thank you very much, madam. Yeah, good afternoon, ladies and gentlemen. I'm now in Indonesia. Now it's around 1 o'clock here. Yeah, thank you very much for the invitation to give the keynote speech here at your esteemed conference, International Conference on Advanced Materials for Sustainable Innovation. My name is Jupiter Harangan Prasada Manarung. I am full professor at School of Mechanical Engineering at University Technology Mara in Shah Alam, Malaysia. I was the former director of SMRI. Now I am the principal fellow at SMRI at UITM Shah Alam, Malaysia, and I'm also adjunct professor at University of North Sumatra in Medan, Indonesia. Now I'm doing my job as the adjunct professor in this week. So the title of my keynote speech is actually on this importance of technology parameters and materials modeling in virtual manufacturing. So this kind of the keynote speech is actually some sort of the sharing experience at SMRI, what we have done, what we are doing right now, towards the elevating in simulations results accuracy. So the content is actually, I would like to begin with the introduction to SMRI, just few minutes on that, who we are, where we are located, what we have, and so on and so forth, And then I will move to the fundamental of manufacturing simulations or the virtual manufacturing. We know right now, the word virtual manufacturing is now widespread, and some inspirations from case studies, from other universities and also from our partners, in Germany and in Austria, because these case studies actually triggered, our research activities more and more, that we would like to do also the same, like they are doing, to the industry and also to the community of the virtual manufacturing. And then at the third part, I'm going to present on our selected past and current research, with our international collaborations at SMRI, and then I will end up with the conclusions. So therefore, this keynote speech is actually a platform. It's a good platform, for us, not only for me to present what we are doing, what we have done, and so on and so forth, but the main objective is actually that we would like to collaborate, with all of you as the participants at this conference. If you are interested, in this doing research, doing collaborations, with us, please contact SMRI, and then we can start the collaborations. All right. So at first, to introduce SMRI. So SMRI is actually a new center of excellence. It is actually established in 2019. But it has a long history. So before SMRI, our center was named as the AMTEX, Advanced Manufacturing Technology Excellence Center. It was also my baby, actually, when I started as the senior lecturer here at UITM Shah Alam. So 5 years after I started, we established an AMTEX, Advanced Manufacturing Technology Excellence Center. And then that one is actually was under faculty. Since 2019, that our top management saw that our improvement, with the dealing with the international collaborations and research, then they gave us some budget, to do the real excellence center under university. So you can contact us also. I put my pointer here. I think this one. Wait, sorry. This one is laser pointer. So this is our contact. smri.uitm.edu.my. And you can also send email to us. Next. Okay, SMRI consists of 4 units actually. So unit 1 is advanced virtual and additive manufacturing. So this keynote speech is actually dealing with unit 1. So unit 2, 3, and 4, I think it is beyond our interest right now. Okay. So we are actually between Kuala Lumpur and KLIA, the airport. So here is Shah Alam actually. So Malaysia, I think everybody knows, between is actually between Thailand, Singapore and Indonesia. This is Malaysia, So I'm now here in Medan. It is not so far away from Kuala Lumpur. Actually, it's only 45 minutes away by flight. Okay, so our facilities, we have actually not so bombastic equipments actually. Maybe you have more equipment like we have here, but we are not only doing actually experimental, but we are also doing the simulations. We call it as the virtual manufacturing. We have some softwares here, such as the Simufac, Modeflow, Sysvel, and also MSC software, and also Altair. So we have some software to do our manufacturing simulations of virtual manufacturing. Okay, our collaborations, international research collaborations, range from Germany, Austria, and also ETH Zurich, and also with industrial partners from Germany, and also partners from the software itself, and also for South Korea also, Okay, so we received since 2013-14 every year around 100,000 euro, yeah, for international research grant until now. This one is from Germany, and this one is from Germany, this one is from Austria, yeah. So this one is from ETH Zurich, yeah. So until now, since 2012, yeah, 13, yeah, we received that kind of grant. So through this grant, this is actually our dreams since many years ago, that we publish internationally joint publications. Yeah. So between SMRI and also our partners. Yeah. This is actually what we are doing. Yeah. So we did the research together. Mostly we are doing here the simulations, and we bring our simulations to Germany or ETH Zurich, and also in TU Graz, yeah, and then we do the experiment here, experiment there, yeah, because we don't have the equipments here, yeah, so we have to have the strategy, yeah, to do the research together, yeah, so that we can publish. Yeah, so we have also journals here, yeah. So we have journals of mechanical engineering. We have Q3 here, Scopus Index, yeah. So that one is under our faculty, yeah, and this one is under SMRI. It's not yet indexed, yeah, but soon, yeah. I hope that within 2 or 3 years time, yeah, we are going to be indexed, yeah, with Scopus. Now it's under the Malaysian index, yeah. So if you have some sort of the research work, yeah, by your degree students, something like that, yeah, or postgraduate students, you can send to us, yeah. Try to publish here, yeah, to encourage our journals also, yeah, to be later on indexed by Scope. So our focus is advanced manufacturing and virtual manufacturing. Yeah, these are actually our equipments. Yeah, we have this one is robotic welding. Yeah, this is actually our bread and butter. Yeah. So now we have a new power source. Yeah, this one is Kempi, our old one. Our new power source is now Fronius. Yeah. So almost every university in Germany, they are using this Fronius power source, yeah. So that we bought also this Fronius, yeah, so that we can on par the level of our research with the European standard. Yeah. So we have also GOM and also some SLM with our partner industries and so on and so forth. We do together also the research. Yeah. So here on down here, yeah, below here, yeah, we have our software. Yeah, this one is actually not not cheap software. That one is quite expensive, but for the educational license, yeah, we can buy this one with our budget, within our budgets. Yeah. So here on this side, on the right side here, this one is open source. Yeah. So we are also doing a commercial software, yeah, like Altes, Simufec, and so on and so forth. Yeah, but we are doing also the open source, yeah, because in Malaysia, in Southeast Asia, the small industries, small company, they don't have any budget, yeah, to buy industrial license, yeah. So that we try to do the open source one, yeah, and then to compare the results with this commercial costly software, yeah. And then we try to solve the problems, yeah, by using open source for the small companies. Yeah. Okay, as I mentioned before, yeah, this keynote speech is not only for presenting what we have done and so on and so forth. Yeah, we would like also to initiate collaborations, yeah, with Indian universities. Yeah. So you can see also here research collaborations between students, research internship, yeah, usage of existing facilities, yeah, software and equipment, yeah, so we can do together and so on and so forth. Yeah, joint supervisions, joint publications between staff, international research proposal applications, and so on and so forth as usual. Yeah. Okay, so let's start with the fundamental of manufacturing simulations, or we call it as the virtual manufacturing. Yeah. With the inspiring case studies from others. And this one is not from us, yeah, but this one is from our partner company universities, yeah, and from other industries, yeah. Okay, first of all, yeah, this virtual manufacturing, yeah, this virtual manufacturing, that one is termed as the next revolutions in global manufacturing, yeah. So the idea of these definitions is actually manufacturing before manufacturing. Yeah. So that we have before we do the mass product or the experimental. Yeah. The idea is to do the manufacturing using simulations first. Okay. So we can compare, between experiment and simulations. Actually, experiment is quite costly, and slow, sequential, sometimes single usage, So by using simulations here, we can have a lot of advantages like cheaper, faster, Parallelization is possible and can be multiple usage. But simulations results are never 100% correct. Because of what? Because of the input data is approximated, mathematical model is idealized, accuracy is limited, and so on and so forth. So there is one this citation from expert. Nobody trusts computer simulations, except the guy who did it. And everybody trusts experimental data except the guy who did it. So why not combine the two and get results everybody can mistrust a little? So this sentence I always present to my students, so that they can have the understanding, before we do the simulations or we do the experimental. This virtual manufacturing is actually a very challenging journey, because there are a lot of conflicting objectives. For example, fast calculations like this, process change, real physics, and simplifications, and so on and so forth. So that's why we need to have a compromise, so that we can do the, our optimized results. But nowadays, interdisciplinary science, is becoming priority. It makes everything will be more complex. So especially, in Southeast Asia and also in Europe, they would like to have this chain process. So what is chain process? I can show to you the results of the chain process. So we can think then later on what kind of the process we can do this chain or couple simulations, we call it. So faster simulations. This is actually the industry. They would like to have faster simulations. So we would like to have precise results. So these kind of objectives are conflict. So that's why we have to have the optimized methods and results. Okay, this is actually the existing simulations fields in the research, because I'm from the mechanical engineering. So we are now still here. So we would like to move to this direction. But the industry would like to say no. So therefore we serve also industry in our research. We are doing applied industry, so that we still in this region, in these fields, by using the continuum theories, maybe a little bit here, phase field, crystal plasticity. Here is on for our research. This one is more for industry. The industry in Europe, they are already moving to here. Mechanical engineering, I mean, the manufacturing. Manufacturing, they are moved already to here. I think soon they are going to move also to these directions. Yes, this one. So this is from Box. Everybody know who is the Professor Box. Is statisticians. From I think from Europe. So they always cited. He cited. Many years ago that he said that essentially all models are wrong, but some are useful. So this sentence is always good to remember, to remind ourselves, so that we know why we start with this. What is the objectives of the simulations? Okay, so in these fields, SMRI is doing here apply. So what we are doing is actually more to the temperature distributions. We move also to the distortions. We move also to the distortion, residual stress, and grain size. This is our research focus actually. This one. So if some industry would like to know a little bit deeper, we move also to here. So we try to do also this flow distributions. That one is a marriage between CFD and also manufacturing. But the industry in here in Southeast Asia, they still refuse to do that. Yeah, sometimes they say yes, sometimes they say no. Yeah, so that they move mostly here. Yeah, in Southeast Asia. I don't know. Yeah, in India, yeah, maybe it is different. Yeah, they move maybe already here and so on and so forth. Yeah. So for the manufacturing, we are still here. Yeah, it is different because my background is actually welding. Yeah, in welding, they like also to see here. Yeah, especially on this crack analysis. Okay, so we try to understand, yeah, what kind of methods, yeah, in the manufacturing applied virtual manufacturing, yeah. So we try to understand, and then we can the objective is actually later on that we say to the industry, yes, we have these three methods. Yeah, which one you would like to have? Yeah. So the first one, which the industry love to use, is actually on this macro, yeah, a macro scale, or we call it as the ISM, inherent strain method, something like that, yeah. And this meso, yeah, meso is TMM, yeah, thermomechanical method, yeah. Sometimes we call it as the thermomechanical metallurgical methods, yeah. If you would like to do the phase transformations, for example, yeah. And this one, the last one is that one is on the micro. Yeah, of course, yeah, there are maybe a nano method, nano skills, and so on and so forth. But at SMRI, we are still here, yeah, because we would like to serve also the industries, yeah, here in Southeast Asia, yeah. So the interesting things is actually here you can see also the computational time. Yeah, here is very short. Yeah, the industry love to use that to hear that. Yeah, it's very short. Or here, yeah. Shorter, yeah, this one, but this one is very long, yeah. And level of details, this one is very low, yeah, this one is low, yeah, and this one is very high, yeah. And the quality of results, yeah, this is actually sufficient, yeah, for the industry, yeah, sufficient or good, yeah. This one is very good, yeah, but this one is the material modeling, yeah. This one is what we are doing, yeah. We are not only focusing on the technological parameters, but also on the material modeling. So the material modeling, if you do the macro, yeah, or the ISF, this one is very low. Yeah, you need only the physical coefficients, yeah, properties. Yeah, here you need also the already the non-linearity, yeah, plasticity, and so on and so forth. Yeah, and here you will need more, yeah, up to the grain orientations and so on and so forth here. Yeah. So this is the possible at the end of this table. Yeah, this is actually the possible strategy. Yeah, for the reductions of the computational time. Yeah, so the lumping layering. Yeah, so the lumping. Yeah, so lumping layering here for the ISM. Yeah, so this is moving meso or layering meso. That one is for the meso TMM. Yeah, and this one is normally we don't do any lumping. Yeah, we cannot do any lumping here. Yeah, so this is what we found out during our research. Yeah. Okay, what is actually lumping? Lumping is actually just to gather, to collect some meshings, yeah, to be a more model, yeah, geometrical model, yeah. For example, here, yeah, we do this lumping methods, yeah, to have this meshing, yeah. That one is to be reduce the computational time, yeah. So here the moving history for the micro, we gonna do the non-lumping, yeah. So here for the ISM, yeah, this is very fast. Yeah, we do the layer by layer, the lumping. Yeah, not like this. Yeah, maybe only 10 mesh elements, yeah, to be one. Yeah, here on this layer. Yeah, this one is very good for the metal additive manufacturing. So our focus, because our focus is the metal additive manufacturing, and we would like to do the faster calculations. Yeah, we try to short everything, yeah, by using this lumping layering, we call it, yeah. So with these simple equations, but also not simple equations, yeah. Okay, this is some inspiring studies, yeah, why we are doing this virtual manufacturing. Yeah, just to go through here, yeah, that one is laser and brazing process. Yeah, so Audi is using also virtual manufacturing for welding the door, yeah, to find out the sequence, yeah, of the welding sequence, yeah. And this is for the brazings also. We can do also for brazing. This is for the self-piercing rivet. That one is the invention from Volkswagen, yeah, in Germany, yeah. So they develop the self-piercing rivet, these innovations, yeah, by using simulations first. Yeah. So at Porsche, they are not only on the process, they are doing also the testing. Yeah. So here we do also the testing for the spot welding, for example, here, yeah, the spot welding, that one is for the SPR, yeah, self-pierce riveting, yeah. So we can do also the testing. We call it as the virtual testing. Okay. This is together with our partners. Yeah, we are doing the warm and rolling. Yeah, so warm is by using shear welding. Yeah, after the welding, we are doing rolling. Yeah, after the welding, we are doing rolling. Yeah, after warm, we are doing rolling. So the objective is actually to have the 100% recrystallizations. Yeah. So before we do that, yeah, so we simulate, yeah, so that we can find out the best welding speed. Yeah, the best welding speed here, yeah, before the rolling. Yeah, so this is actually the idea to use the virtual manufacturing, and some software they allow to do that kind of the investigation. Okay, this one with the German partner also. Yeah, this one is more to the bipolar plate for the fuel cell. Yeah, but that one is for the using metal. Normally by using graphite. Yeah, so they do also the wrinkling, defects analysis, and so on and so forth. Here is without virtual manufacturing. Here is with virtual manufacturing. Yeah, so you see also here the quality, yeah, of these products. Okay, this is between isotropy and anisotropy. Yeah, so you see also, yeah, the difference, yeah, between if you do the material modeling very simple like isotropy here, if you do the anisotropy here, yeah, you see the results is different. Yeah, okay. So this is our partner also in Australia. Yeah, they use also the virtual manufacturing to find out. Yeah, that one is for the SLM, yeah, selective laser melting. They would like to find out which one is the speed, yeah, the best speed, yeah, so that the results, yeah, the result of the materials, yeah, to have this ultrafine lamellar alpha beta microstructure. Yeah, so they found out that the speed must be, yeah, between this, yeah, this value, yeah, so that you can have, yeah, this kind of you can achieve this kind of objective. Okay, this one from TU Technical University Dresden. Yeah, this one not only for metal, it's doing wood. Yeah, this one is for the Mercedes-Benz. Yeah, in Stuttgart, is also with wood. Yeah, so meaning that the future manufacturing not only for the steel but also for the wood. Yeah, and we can do also some other materials. Okay, so. I think I still have 10 minutes. Yeah, so I would like to present on this our research. Yeah, so this is our past and current research. Yeah, with the international collaborations. Yeah, at SMRI. Yeah, with the hope that after this keynote speech, yeah, I'm waiting for some emails, yeah, or WhatsApp, yeah, to discuss on the further collaborations between India and Malaysia and also Indonesia. Okay, the first one, our past research projects with German is actually just to simulate. That one is a project from industry, yeah, just to simulate, to couple process, yeah, simulations between forming and welding, yeah. So the idea is sometimes, many times back, that if we do the couple process, we cannot do it because sometimes we do the forming first, yeah, and then we do the welding. Now the idea is we would like to transfer all of the materials, yeah, from the forming, yeah, the defects, materials, residual stress, physical properties, and so on and so forth, transfer it to the welding, yeah. Then we do the welding, and then we see, yeah, the results, yeah, without transfer and with transfer, is it a difference or not, yeah. So we have done this one in at our university because we have the robotic welding, yeah. So go faster here, yeah. This is the actually, oops, I cannot. Minutes pointers, I have to stop it. Oh. Okay, so yes, yeah, this is the forming, yeah, this is the forming, yeah, still forming, yeah, so still forming, yeah, so and then we do the welding, yeah, but all of the materials, yeah, the change of materials and so on and so forth, we move to the welding, yeah, so that the reality, yeah, it will be represented, yeah, at the end of this at the end of the process simulations. Yeah, we do also the distortions. There's also residual stress here. Yeah, and the end of the day here, yeah, you can see. Oh, sorry. You can see here, yeah, the different without the forming history, material transfer, and here the with forming history. Yeah, so that we know that the transfer of the material modeling, if you do the couple process, yeah, it is very, very important. Okay, so we do also deep drawing, yeah, with the damage model. Yeah, this one is in Nakajima test. Yeah, this one is very costly. We don't have this kind of testing equipment, so we did it in Germany. Yeah, so that we do the FLD. Yeah, but with the limited specimens. Yeah, I think for the Nakajima we need 7 or 9 specimens after that. We do here only 3. But this is enough. Yeah, with our algorithms. Yeah, with our the mold design and so on and so forth, it is enough, yeah, actually to see whether the defects, yeah, can be modeled or not. Yeah. Okay. We are not only using the simulations just only for the technology process parameters, yeah, but we are also doing the subroutine. Yeah. So this is actually the mother of the softwares. Yeah, the subroutine must be correct. Yeah, so sometimes the software cannot be used for our applications because the subroutine is not there. Yeah, the application is not there. So that we have to develop our subroutine itself. Yeah, that one is projects. Yeah, also from Germany. Yeah, just to write the subroutine for the laser welding. Yeah, so that we can evaluate, analyze the hardness. Yeah, the hardness of this metal part, yeah, if we weld by using the laser welding. What we need here is, of course, CCT diagram, yeah, and the CCT diagram must be read later on with our subroutine, yeah. Okay, so here we use the Seyfarth-Kasatkine here, yeah. This is a non-isothermal one, yeah. Sometimes the people are using the isothermal, yeah, Johnson JMAK, yeah, Johnson Mel Aframi Kolmogorov, yeah. So this is for the isothermal. So here we do the non-isothermal, yeah, because we are more doing the CCT and so on. So this one is for the TTT diagram, yeah. So sometimes people convert from the isothermal to the non-isothermal, yeah, from TTT to CCT because they need CCT for the welding process or additive manufacturing process, yeah. So here is our discrepancy. It's around 10 to 15%, yeah, on this hardness, yeah, compared to the CCT, yeah. So of course this can be the improved, yeah. This can be improved, yeah, the algorithm and so on and so forth. Okay. So we are also do the predictions of the grain size, yeah. So this one is also not easy, yeah. So we do the using the equipment in Germany, yeah. Here we have, yeah, this one we have, yeah. This one, this facility we have. Sorry. Yeah, this facility we have, yeah, but this dilitometer, we don't have this one, yeah, so that we are doing the collaborations in Germany. So grain growth models, we collaborate with Cambridge University. They develop this kind of grain growth model, yeah, so that we use the subroutine actually with this algorithm within our subroutine, yeah. So we use the Runge-Kutta, yeah, 4th order, yeah. So and then this is actually the I think 5%, yeah. So the error of percentage is 5% here, yeah. So it is quite good for the basic research, yeah, for our master and degree students. So sometimes we do also probabilistic, because of what? Because the FEM is actually, if we do today, yeah. So and then if we do tomorrow, the results will be similar. So we call it as deterministic. But in the industry, yeah, it is not like that. Yeah, today you do the experiment or you do the productions. Tomorrow is different. Yeah, so that we include the Monte Carlo, yeah, method. Yeah, so that we can have this probabilistic FEM. This is actually one of our research. Yeah, to do the Monte Carlo methods not only for the grain growth. Yeah, so this one is the Monte Carlo. It's very simple one actually. Yeah, not only for the grain growth we do. Yeah. But for the grain growth here, yeah, probabilistic simulations gives a little bit more result, yeah, for that, yeah, compared to the deterministic simulations. Yeah. So another one for the meso one, yeah, meso scale, yeah, we are doing the distortion analysis. I can go faster here, yeah, for the SLM, yeah, we do the ISM, yeah, macro scale or inherent strength methods, yeah. We do also for the WOM, yeah, wire arc additive manufacturing, yeah. So we try to understand what is the difference between TMM, yeah, ISM, wet with the wet kinematic or user defined. Yeah, of course TMM is the best, but the computational time is the longer. Yeah. So we do also the distortion analysis with MOM, but yeah, we do also the material modelings. Yeah, between the we compare, yeah, between the simulation database here, yeah, and the material model from the filler wire, yeah, and then the material model from the component. The best one is actually from the component. Yeah, you see here. Yeah. So now we know that the range of the error, yeah, if you do the simulations by using software, yeah, or filler wire, but also the component, we know actually with this all of experience, yeah, you know, somehow the range of the error. Okay. So I go faster. The one is from the aerospace industry for the bracket. Yeah. So here by using TMM, yeah, the simulations, the error is 1.85%, but the computational time is 14 hours. Yeah. And we try to understand by multi-scale, we combine macro and meso-scaled, yeah. So we don't want to have the calibrations because the ISM, normally we need the calibrations, yeah. We would like to have, to simulate the calibrations. Here we call it as the virtual calibrations test, yeah. So by using this one, yeah, so we have a 5% for the TMM, yeah. Combined is 8%, yeah. Combined is 8%, yeah. So this is from Cambridge, I think. Yeah, from Cambridge, the result from Cambridge, yeah, 5%, yeah. Here is pure TMM from our side, yeah, 4.6 minutes, yeah. This is no report on that, yeah. Here we have 129 minutes. So this one is combinations. Of course, this is a little bit higher, yeah, 8%, but the computational time is quite half of this one, yeah. So now we know the selections of macro, meso, and also micro later on, and then we can present to the industry. Yes, we did this one. Yeah, what kind of methods you would like to choose? Okay, this one we do also for this bracket. Yeah, by using the multi-scale, you see here. Yeah, the result is 5.5%. Yeah, compared to the TMM is 1 point something %. But here you see here 5 hours. If you compare to the computational of the mesoscale simulation, this is around 14 hours. Yeah? 5 hours is quite sufficient for the industry. Okay, so we do also warm, yeah, without substrates, yeah, for using the mesoscale simulations. I hope you can understand, yeah, what is actually meso, at least, yeah, macro and micro in our case, yeah. So we do also here, yeah, percentage of error is around 3%, yeah, on that one. So we do also DED for laser powder, yeah, Inconel 718, yeah. So this is actually, we would like to do the collaborations with this guy. Actually, the one is from the Nagpur, actually, yeah. So from India here, yeah. So we don't have any collaborations. They did the experimental, yeah, and then we try to simulate what they have done, yeah. So we would like to try, because we don't have the equipment, yeah. So we try to simulate, yeah. So, and then we find out that our simulations is also quite good here. Yeah, this one must be something for the adjustment later on in the simulations, yeah. So this one is also the good result we can get from the simulations, yeah. I think I need to contact them and then to discuss, maybe we can have the joint publications with them. So this is with the another university also, yeah, simulations of experimental distortions for the laser cladding, yeah, in Cornell 625, similar, yeah. So they have their experimental study, yeah. We do the simulations, yeah. We do the simulations and then we try to combine together, yeah, later on, okay. So this is new for us, yeah. That one is for the pipe flange. Yeah, we do also the pipe flange here for the oil and gas industry, yeah, by using the wire arc additive manufacturing. Yeah, so before we do that, yeah, we simulate first and we want to see the residual stress, distortions, and so on and so forth. Okay, also casting, we do also the casting process. That one is a good project from industrial partners in Malaysia, yeah. So we would like to know the cause of defects, yeah, actually the risers here, we can move here and there and then do the analysis on it, yeah. So this is for the post-weld heat treatment, mechanical treatment we call it. Yeah, this one to extend the fatigue life. Yeah, by using this equipment HFMI PIT here. Yeah. So before that, we would like to confirm that our simulations we can simulate the results of this impact. Yeah. Okay. So just I need 1 minute. Yeah. Current research. Yeah, using virtual manufacturing. So I put here. Let's collaborate. Yeah. So that I hope that after the end of this one we can collaborate. Yeah. So what we do right now is our current research is actually for the wire arc additive manufacturing. Actually, the idea is we would like to define, we would like to customize the phases, after the wire arc additive manufacturing, So, for example, here I would like to have to have more ferrite, perlite. Here is more binite, so that we can do this, So at the end of the day, So for that also we do some simulations, So by using TTT and so on and so forth. Here first the residual stress, and then we found out that this one is not enough. We must do the experimental. That one is with the Sweden University actually. They did it the experimental a long time ago. They don't have the result right now anymore. Because they throw away already. So that we try to understand with these small parts. You see here, with the 8 millimeter per second welding speed, and here is 15 millimeter per welding speed. So here the experiment we can get the 180 to 280 hardness figures. Here simulations 290. So something is wrong here. So that we need to adjust. We need to do it. So we need to improve our simulations. How do we improve that? If we do the experiment, that one is very expensive, and now we do the fitting. So for the first step, our degree student and master student, they do the fitting first. What do they do actually for fitting? So fitting is actually not different as this one. So this one is the CCT diagram. So this is the data we get. So that we like to change the fractions and so on and so forth. So by having the real hardness, and then we do the calculations and so on and so forth. So that we get not so much data here. For example, wait a minute. Here this one is already fitted, but fitted with knowledge. Not only just put ferrite, perlite, and so on and so forth. There is a calculations on that, equations on that, so that we can have, and then here is the original one. That one is fitted, that one is hardness. That one is original, and this one is for 15 millimeter per second. That one is for the 8 millimeter per second. So remember here, the first picture. This one is on the simulations. The first simulation by using database. So here is our simulations fitted. By having improvement of the CCT diagram. So this one also. So meaning that we have to do the material modeling, so that we can elevate our simulations results later on. Okay, for the spot welding also, we do also some research here. So we do also for the flow curve, material modeling. The most important things is the contact conductance, thermal contacts, electrical contact conductance, thermal contact conductance, electrical contact conductance. This contact parameters, coefficients is very, very important, but very difficult to do. That's why we still in this stage, we do the research on the literature, on the journal to get these coefficients. Okay, here is the results. So this is the result from the journal, 3 to 3.5 millimeter diameter. So we got here 3.2 millimeter for the nugget size. Okay, so I move faster here because I don't have time. So we do also the ultralight component by using lattice structure. We do also here, the testing here, virtual testing we do. You see here, So we do the virtual testing. We see then later on the cracks, where is the cracks, and so on and so forth, and we compare it on. This is for PLA, simulations of the 3-point bending. 3-point bending. Also, we do the subroutine and so on and so forth. You see here we try to understand, where the crack starts, and then so on and so forth. And then try to compare with this. This one is from the experimental. That one is with the Cyprus University. This one they did it. Experimental. Here is our experiment. Of course, It is not yet perfect. Yeah, we still to do here and there the simulations. Okay. So the physics DOE, meaning that this one is DOS, design of simulations, we call it, because we already know the range of the error in any aspect. Yeah. So that we try to do the design of experiment. Yeah, we would like to replace the, instead of the design of experiments, we call it as the design of simulations. Yeah, or we call it as also as the physics DOE. Yeah, in the material science also, yeah, we do the artificial neural network, yeah, for the damage modeling. Yeah, so here for the Johnson-Cook damage model, we try to get rid of this damage model. Yeah, so we try to do it by using the artificial neural network. Yeah, this is also our research later on. So this is on the costing also. We do also the costing, warm costing we do. Yeah, this is actually not different as the welding. Yeah. So this one is for SLM. We do also the SLM costing. Yeah. So a very comprehensive one. At the end of the day, we would like to have this one. Yeah. When we can get the cheapest, how many quantity, yeah, the cheapest price. And you see here, if we do only one, for example, for the metal additive manufacturing, it will cost you 4,500. Yeah. Now, yeah. So here, yeah. So if you have 9 or 11, yeah, the price is quite stable. Okay. So this is the next digital repair, we call it, yeah, using SWARM. Yeah. So also the welding design and stress analysis we do also, yeah, by using the ANSYS. It's also not easy. Yeah. So which one we have to, which throat thickness and so on and so on we have to define and so on and so forth. Okay. Just for the conclusions, yeah, very fast. Yeah, dealing the couple process, transfer considerations, geometry, material is very important. Material model is very important. From database, you can get 20%. Yeah. Feedstock is from 10%, evolved component is 5%. Yeah. So also the heat source model is very important also. Yeah. Oh, very slow here. So okay, combine scales. Yeah, it can save time. Yeah. So and then probabilistic FEM is also coming soon. Right now, yeah, intelligent FEM also with ANN must be also considered. Yeah, in this IR 4.0 era. Yeah. Crystal plasticity also, yes, is also in our focus. Yeah, yeah, interdisciplinary collaborations is needed. Yeah, so for us as academicians, yeah, of course, this graph is very simple. Actually, what we need, yeah, if we would like to master the virtual manufacturing, of course, numerical in the team, you have to have a numerical method expert, material expert, yeah, technology expert, design, and also a little bit on the programming language. Sure. Okay, that's all actually from my side, ladies and gentlemen. I hope you don't get bored with this. Okay. All right.
Thank you so much, sir, for sharing your valuable insights and expertise with us today. Now we are open for Q&A session. If anybody is having any query with sir, please come to the podium and you can ask your question. Among the audience, if anybody is having any query with the sir, you can come to the podium and ask the question to him. Moving on, thank you so much, sir. We greatly appreciate your time and wisdom you have imparted in us today. We look forward to hearing from you in the future as well. Thank you, sir.
Yes, thank you very much. Yeah, please contact us. Do contact us if you like to do collaborations. Okay. Thank you.
Thank you, sir.
Okay. Bye.
Continue to explore groundbreaking advancement in science and technology. I am delighted to introduce our next esteemed speaker, Dr. Umesh Kumar Tiwari. Dr. Tiwari is distinguished scientist and academician with an impressive background in fiber optics, optical communication technology, earning his PhD from the prestigious Indian Institute of Technology, Delhi. Currently serving as a senior principal scientist at the Micro and Nano Optics Center at CSIR Central Scientific Institute organization in Chandigarh, India. Dr. Tiwari also holds the role of professor at CSIR Academy of Scientific and Innovative Research in New Delhi and is the chairman of the Institution of Electronic and Telecommunication Engineers, IETE Chandigarh Center. With over 130 research publication to his name, Dr. Tiwari's work has significantly impacted the field, garnering over 2,200 citations and a 26 H index. Dr. Tiwari's current research interests are focused on cutting-edge areas such as quantum photonic integrated circuits, fiber Bragg grating-based sensors, quantum technologies, optical metasurfaces and metamaterials, optical tweezing and trapping using fiber nanotips, FBG-based accelerometers and acoustic sensing, and LPG-based biosensing, including applications in bacteria, pesticides, biomarkers, and antigens. We are honored to have Dr. Umesh Kumar Tiwari with us today. Please join me in welcoming him to the stage to share his insights and expertise on the topic optical fiber biosensors, present and future perspectives. Over to you, sir.
It's indeed it's a great pleasure and honor to me to be here. I'm also very thankful to the organizer of this conference, international conference on advanced material for sustainable innovation. So I'm here basically we have worked on various sensing platform, particularly on optical fiber based sensors that we have simulated, manufactured, developed, tested. But today I'm sharing some of our work on the optical fiber biosensors, like what is the current is going on and what we can do in the future and how they can basically make the innovation for sustainable development. So basically I'm belonging to a great organization that is called the CSIR, Council of Scientific and Industrial Research. As far as the students is concerned, they know CSIR as a body who is providing the fellowship for their research, their PhD, and of course some of the grants to the faculty members in the across the country of various institutions using different funding modalities. So actually CSIR is having almost 39 laboratories across the India, and they are working in various all the areas, whether you talk of material science, aerospace, biology, medicine, plant, instrumentation, semiconductor, you name any area. So the CSIR labs are there, and they are making their footprint, and they have made lot of innovation, and they have provided lot of technology to the country. All of you know, like during the election, there is a ink, indelible ink, and that ink is developed by the CSIR, one of our laboratory. Even the this milk powder was when there is a scarcity of the milk in the country, the CSIR, our one of the sister laboratories, they have developed the milk powder at that time, right? So we are working in many fields like healthcare, agro, food, chemicals, ecology, environment, earth sciences, aerospace, mining, material, housing, construction, everywhere, right? So about the CSIR, like about our own laboratory, so its origin is like from by the Planning Commission, established in 1959, and this is the picture of our first Honorable Prime Minister, Jawaharlal Nehru, Pandit Jawaharlal Nehru. So our laboratory is basically working in certain areas like agriculture, healthcare and public safety, energy monitoring management, of course optics and photonics, strategic instrumentation. So actually optics and photonics is my domain, and basically some of the unique strengths of my laboratory is like human resource. We are having the CSIR, so which is providing the PhD for the science and engineering students. We have a PRISM scheme, so where the some of the startups or innovators, they can submit the proposal. If the proposal is very innovative and it's doable, so they can get the funding up to 20 lakhs, right? So that is also one of the very unique scheme in the country, which is our laboratory is also one of the nodal center, and it is from the DSIR, Department of Scientific and Industrial Research. And also if your proposal or maybe if it is then you have demonstrated a prototype, then further you can get the funding of 50 lakhs for the startup. Then we have a skill development. So through the CSIR and skill India Skill Innovation, we have one of the unique Indo-SIVS Training Center, where we are providing the diploma, so 4-year diploma to the students. So we have a very good capabilities, so which can cater the MSMEs. So so this is my like I have enlisted my talk, like I have just give an introduction, and then what are the fiber optic sensor. I know many of the students, they are from the IoT background, like they are doing the IoT, BTech in IoT. So sensing or sensors are very important for the IoT, Internet of Things, because without sensing integration and their basically emulation, like you can't do the IoT, whether it is agriculture field or any public safety or anywhere. So sensors are the integral part of our IoT platforms. So and then of course, because I am talking on biosensors, right? So I have to just introduce how to make the optical fiber as a biosensor, and then of course I have covered some of the things like these are the different kind of fiber platforms, like they are called the different names, like multi-mode fiber brake grating, and then I have given some case studies like we have used for this sensing platform. For example, for the bacteria sensing, and then biomarker like triglyceride, we have also detected the triglyceride. Then we have, because this conference is related to material, of course this talk is slightly different, because I am not talking about the material like how our previous speakers, they have spoken about the material of the magnesium to many good novel material. So of course, but we have used these materials to exploit their good features to get the good sensing modalities. Then of course, because I am talking on the optical fiber, but the future is basically on chip photonics biosensor. So I have also included some of the on chip sensing platforms and how they can be simulated and how they can be fabricated. So and of course initiative also have covered the initiative towards the on chip photonics, what we are doing in the CSIO, and then conclusion. So as you can see, the sensors are the device like which can convert one of the physical parameter to the magnitude of a second different parameter, which can be measured more conveniently and more accurately. And as we know, like these are the different sensors people are using, and as we know, during COVID-19, in every household the people are using the pulse oximeter to measure their oxygen content, right? And that at that time it became a very important device for everybody, right? And then in the older time, in the mining, people are using this bird just to detect the methane outburst in the mine industry. Thermometer we are using, like glucometer everybody using to detect their diabetic condition. And this one of the COVID-19 kit was developed by our sister lab in the New Delhi IGIB. So it's a paper strip, so that can detect the COVID. You know, like importance of the sensor research, because we know like there are lot of pollution through the industry. Then of course, you know, there are lot of pesticide people are using in the agriculture. So you should know like what is the label or what is the contamination of the pesticides, whether it is a permissible level or not. So you know, they all are posing a lot of threats to the human life. And of course the industrial based, because the industries are due to their you know, they are due to their profit and all, they are not looking how they are polluting the environment, our water bodies, and also you should also detect the water contaminations. Then bacterial infection, people are also on a present day talking on the food safety. So there are a lot of people are using the sensing modalities to detect the food contamination. And of course there is a lot of market for the sensor research. So and it is keep on growing. For the students, like these are the some of the parameters, like how you can define like a good sensor is, because for the researcher also these are the some of the parameters like sensitivity, figure of merits, quality factors, signal to noise ratio, limit of detection. So how like people are researchers, they are using in the all their studies and also in their research papers. So if you don't have these parameters in your research papers, so definitely reviewer will ask you to do all these things. So then only that paper can be considered it's a good quality. Okay, so these are the some of the process for how you can classify a biosensor. So a biosensor is basically it consists of bioreceptors, which is called the biorecognition molecules, right? It can be antibody, it can be aptamer, it can be biophos if it is a bacteria, it can be many kind of bioreceptors are there. And then there is a transducers. Transducer can be the amperometric, optical, then fluorescence, many kind of transducers are there. So then by integrating both of them, they can become the biosensor. Like you have you wanted to detect some bacteria, you need to have some antibody, the bacteria will come, and then that particular antibody will interact only with that particular bacteria, and then that can change the signal, and that the signal, the change in the signal which you are want to detect, the signal is basically the your transducers, like whether you are detecting in terms of the current or in terms of the fluorescence quenching or fluorescence enhancement, or maybe change in the wavelengths, or maybe the change of different kind of signals. So that can be the become the complete biosensor. Okay, so these are the I have also covered, like because I'm talking about the optical fiber. So these are the some of the research groups in India, like IISc Bangalore, IIT Patna, IIT Delhi, and many others, like many other labs also, they are working on the optical fiber based biosensor, right? So they have detected like E. coli bacteria, then they have also used this grating for the this sensor of sensing of the temperature and strain. Then they have also used SPR sensor for the cancer cell detection. So these are the some of the groups, those who are really working in these areas, right? So then I'll come to the optical fiber sensors. So optical fiber sensor is a sensor that measure a physical quantity based on the modulation of its intensity or spectrum, phase, or maybe the polarization of the light traveling through the optical fiber. Like any change, like let's say if I have optical fiber, so you all know the optical fiber is used for the optical communication. So like we are enjoying all this kind of video, and then very high bandwidth in the mobiles. So that backbone is basically optical fiber, which is carrying the terabytes of signals, right? So optical fiber is very small in dimension, like 150 micron diameter, and the 250 is total diameter, including its outer jacket. But when we are using, so its dimension is as you can imagine equivalent to your human hair, right, but it is carrying a lot of signals, right. So, similarly, like when there is a change in the intensity, like the light traveling to the optical fiber. So, the people are, you can make they are making the optical fiber itself as a sensors, like if you send some light and you detecting at the end, and if there is change in the signal, so it can make a intensity based sensor, like people are using intensity based like pressure sensor or maybe the temperature sensors. So, similarly the phase are like for the interferometer polarization based and wavelength based, but the advantage, if you talk of advantages, so optical fiber they have lot of advantages as compared to the conventional sensors, whether they are the strain gauge electrical sensor. So, the most important advantage is optical fiber is made of the silica. So, that is basically a kind of material which do not have any impact of the RFI EMI radiation. So, even if the, let us say if you have some environment where you have some electromagnetic interferences, right, or maybe the some of the environment like where the electromagnetic pulses like nuclear radiation environment. So, where the conventional sensors they are not working, right. So, the fiber optics, because they are insulator basically, right. So, you can use those kind of sensors, like you have sensor. So, and another advantage is the sensor and the channel is the same, right. The sensor itself is a channel. So, the fiber is a channel also and it is a sensor also. So, you do not need to have a separate kind of line to send the signal, right. So, and then it has a multifunctional, like you can make in one signal fiber different sensing modalities. So, you can, one sensor can sense the temperature, one can sense the strain, one can the pressure, one can the vibration. So, like in one single channel a person can use the multifunctional capabilities. Remote accessible. So, the optical fiber that is having the 0.2 dB per kilometer losses. So, you can monitor from the kilometers of distances, right. So, like you can have your station monitoring station somewhere else and the site somewhere else, then also you can use this kind of sensing platform. Okay, so, these are the, I have also just have some introduction of the what kind of sensing platforms. So, and that is just because the students they might not knowing. So, these are the fiber Bragg grating. So, Bragg, you know, like the Bragg, the name of the scientist, right, who has given the Bragg principle, right. So, about the Bragg diffraction, right. So, similarly the similar principle have been used in fiber Bragg grating, like fiber is the optical fiber, Bragg is the, because it is working on the Bragg condition, and then grating is the periodic structure. So, because these are the periodic structure, right, and that we have created using the UV light, because and this structure was created in the core of the optical fiber, and these structures of the nanometer dimension, like they are the 500 nanometer, and that we have created using the interference UV lithography, right. And then this structure basically, if you send, let us say a broadband pulse, right. So, it will not allow to pass all the wavelengths, one wavelength is reflected back, for which this structure is created, and all other wavelength they pass through. So, they are also working as a wavelength filter. So, this kind of device used in the optical communication also for the eye drop multiplexing, right. If you are going your signal or your one channel is going from Delhi to Chandigarh and you want it to drop in somewhere, so that this can be used, so that the channel will be dropped. If you want to add at some location, that can be used for the adding the channel. So, that is the communication perspective, but for a sensing perspective, basically if I use this device as a strain sensor, so I can just surface mount it or maybe embed in the some structure. So, if the structure is experiencing, let us say some beam is there, like for the structural health monitoring in bridge or in a building. So, if the bridge is experiencing some stress or some bending, so there is a change in the its periodicity, and then there is the shift in the wavelength, and then one can detect the something is happening in the structure at that particular location. Another kind of sensor is basically long period grating. So, why that is called the short period grating? Because that periodicity is of the nanometer. Here the long period grating, the periodicity of the order of the micrometer, around 100 micrometer to the around 600 micrometer. So, here the thing is like those sensors which I have discussed, they are the reflection based sensor, right. So, you have sent some light, and then one of the wavelength is basically some particular color, right. If you have sent, let us say 10 colors, so then one of the color is reflecting back, right. So, these sensors, because they are working in the reflection mode, and these sensors, because here the thing is like because of this periodicity of the longer period. So, the core mode power is coupling to the cladding mode, and then you have evanescent field is available on the surface of the optical fiber, and if you wanted to detect some of the biomolecules, so you just modify this surface. If I think this is not coming, mouse is also not coming, right. No problem, okay. The pointer is all not coming because pointer is all this. No, it's not working because it's not a screen, this is TV. So, it's absorbing light, it is absorbing light basically, right. Okay, so no problem. So, this part is basically we can manipulate using the bioreceptor, and then you can apply any kind of analytes, and then there is a change in the wavelength. So, that basically become the sensor. Another important sensor is surface plasmon resonance, right. So, where the optical fiber surface is coated with the nano layer of metals. Metal can be the gold, silver, right, or maybe ITO, right. So, depending upon that at what wavelength range you wanted to operate. So, people are coating generally gold, right, using the sputtering method. It can be the thermal also, or it can be the magnetron sputtering. We are also having the magnetron sputtering in our institute, and it is basically customized. So, because the optical fiber is cylindrical structure, it is not the flat structure. So, we have customized in that way, so that there should be a uniform coating on all the surface of the optical fiber, right. So, the thing is like once you coated any material like gold or silver, and when your EM wave, electromagnetic wave, is interacted with the metal layer, so the free electrons, they will be basically start oscillating, right. So, because of the oscillation of the electrons, they generate the surface plasmon wave, right, and the surface plasmon waves, it is basically die out in the this one, and then you can get in the air, and you can get this kind of resonance wavelength at the output, right. So, these are the output spectrum, right. Then important thing is, okay, now you have done everything, okay, you have coated your surface of the fiber with the antibody and with the your bioreceptors. But how do you know like whether really there is a uniform coating, it is done or not done? So, then there is some of the characterization techniques. So, we have used the confocal microscopic just to analyze the protein attachment, like whether really the protein attached or not on the optical fiber surface. So, you can see because of the confocal microscopy that the protein is interacting with the laser light, and then it is fluorescence, this green fluorescence. So, then that is the basically confirmation that the protein attached on the optical fiber surface, and also people are using the Raman spectra for the antibody coated optical fiber. So, that Raman is also giving the peaks for that particularly antibody. So, that is the basically for the confirmation purpose. Now, just I will take you through some of our studies what we have done. So, using these kind of optical fiber. So, like we have used first fiber Bragg grating, okay, for the Salmonella typhimurium. It is one of the kind of bacteria, right? So it's a very dangerous bacteria. So that we have just for our just to test the platform, whether how much the sensitivity is there, how it is, whether really it is the sensor is working for this kind of detection of the bacteria or not. So what we have done, these are the some of the like design recipe. So where you can see like we have taken the optical fiber, and then we have fabricated the sensor also, because we have the facility to fabricate the sensors. So we have fabricated using UV light. So the sensor is sensor was created in the optical fiber core, and then the thing is like we have used the basically that is called the covalent bonding, right? Directly it is not attached on the optical fiber surface, right? You can just deep, so it won't. So we have to use some of the chemistry, right? So that is called the covalent bonding. That is also called the EDC NHS chemistry, right? So the chemistry people, they know very well, because I'm not from the I'm not a chemist. So we have our collaboration with the chemistry department. So they have used this chemistry, covalent bonding. So basically they have first used the Piranha solution, that is the H2SO4. So that's to generate the hydroxyl ion on the optical fiber surface. Then we have used APTES so that it can generate the NH2 group, amine group. And because amine group is having a very good affinity, so with the this carboxyl group of the your antibody, so that is how that antibody is attached with the CO bond of the carboxyl group. And then we have a bacteria culture, like the students have performed. So and those bacteria, they are the non-pathogenic. They are not, because to handle and just for the safety purpose, we have one of our laboratory in the Chandigarh, that is called the Institution of the Microbiology lab. So they have basically cultured and they have given these bacteria, but we have ensured that they should not be pathogenic, otherwise they can create problem to the human being. So we have used the non-pathogenic bacteria just for the this testing of the sensing platform, and then we have detected the this bacteria. So you can see like these are the some of the tests we have done after, because we have reduced the diameter of the optical fiber. So we have etched them using the hydrofluoric acid, and then we have used the same images, right, like to just to see that their platform, their surface profile, right. And then you can see here the optical fiber, the portion, half of the optical fiber was etched. So these are the some of the, you can see the result, because all the optical fiber based sensor, they are the refractive index based basically, right. They are sensing the change in the refractive index, that is the very sure, right. So they are all refractive index based. So you can see like we have first basically here you can see these are the RI solution we have prepared, and then we just tested like how much the change in the wavelength. So just to calculate the sensitivity, right. And then because these sensors, they are also equally sensitive for the temperature. Like if you have sensor and then you are want to detect some of the biomolecules, so you don't know whether the shift is because of the temperature or because of the some molecule is there. So that we have also tested for the temperature. So what we have done, we have made in such a way, so the half of the sensor where we are not applying any solution, so that is sensitive only for the temperature. The other part is sensitive for both temperature and the bioactivities. So the amount of shift what we are getting from this portion, that can be subtracted, and that the sensor can be make the temperature insensitive, right. So that also we have done. So these are the like you can see like we have detected very small quantity. The CFUs, they are basically classifying the bacteria colony forming unit, because the bacteria, they are forming the colonies, right. So that is called the CFUs. So then we have detected the 10 CFU, 20 CFU, 30 CFU. It's a very small quantity, right. And then you can see here this portion is enlarged there. So then we are getting very good shift in wavelength, and here there is no shift because of the portion which is not etched. So then there is no bioactivities. So these are, and then also the important thing is, so you don't need only have to do the sensitivity study, but you have also do their selectivity and specificity studies, right. So then in the last graph you can see we have also, because we are using the antibody of that particular bacteria, and then we have applied the different bacteria also, like Cerosus and then E. coli, A. cerosus. So they don't have much shift in wavelength if we are putting these bacteria. So then these antibodies and these sensors, they are also highly selective for that particular bacteria, right. So we have then come up with the sensitivity around 15.7 nanometer per RIU change, and then LOD is the 7 CFU per ml. So basically the sensitivity, if you are calculating, it's a very absolute quantity, but LOD is a basically statistical quantity. So it is calculated from the standard deviation and also. So this is like it is a standard deviation. So it's a statistical quantity, right. So that one must keep in mind, like what you are presenting, right. Then another sensing platform, as I have demonstrated the long period grating. So where the long period grating also we have tested. So long period grating platform, we have done one of our collaborator in South Delhi, so Professor Inakshi Sharma. So with them we have done a study on the tricrystallite detection, right, and this study was very also appeared in the one of the very reputed journal, Biosensor and Bioelectronics. So here same, the chemistry is same as I have explained, that EDC NHS chemistry, only the sensing platform is different, okay. And also we have shown, sorry, also we have shown like when you have prepared your and we have used the lipase enzyme for the detection of the your tricrystallite, right. So you know, like TG is also very important biological parameter for everybody. Now if the TG is high, then it also enhances the risk of stroke and heart attack, right. So this just like for the testing. So you can see like we have done very good study in terms of like at what pH value the enzyme is giving the maximum activities, right. So then the pH value is 7.4. At that pH value, black graph is there. So you can see we are getting a maximum sensitivity of the sensor at the pH value of 7.4, right. And the best response sensor at 4 mg per ml solution of the lipase enzyme, like it is not like you have to use any concentration of the lipase enzyme, right. At this particularly concentration, you can get the better or maximum sensitivity, right. So now I have spoken about the EDC NHS chemistry and covalent bonding, but one of the very good material, right, the scientists are using this MOS2 material in many like even in energy harvesting and in solar cell and in many other application people are using the MOS2. So what we have done here, because if you are using this MOS2 and if you immobilize or coat on the optical fiber surface, so we don't need to have this EDC NHS chemistry, the covalent bonding is don't need, right, it is not needed. Directly the antibody is directly attached on the MOS2, that is the because of the surface, the free surface group, they are very good. So basically you don't need any cross linker, right. So this, so here you can see this molybdenum disulfide. So people are using in many other application. So we have prepared this nano sheet using the sonication techniques, right. So, using these nano sheets, we have used the MOS2 solution, and then they have attached on the SPR 5 sensor surface. So, you can see here. So, these are the like you can see we have used gold coated optical fiber, and then MOS2 is attached on this surface, because the gold is having very good affinity with the sulfur. So, then that is attaching very nicely, and then antibody of the bacteria is also immunocomplex, it is attached with the this MOS2 matrix. So, it is giving the two advantages. One is basically we are not applying any covalent bonding chemistry. So, directly it provide the attachment of the antibody with the 3 sulfur group, right, and it also enhancing the sensitivity, because the MOS2 is providing the bigger surface to volume ratio, right. So, that having the more binding sites, right, more binding sites. So, then that is giving the some of the good advantages. So, these are the like we have first done the control experiments when there is no antibody, without antibody, it's like we have tested. So, then you can also see there is no shift in wavelength, right, and though no significant change is evident, right. So, here again we have done the comparative study, right. So, you can see for the E. coli, like one is for the without antibody and one is for the with the antibody, right. So, here you can see this is the lower graph, it is with the antibody and gold surface and fiber, right, and that is without the antibody. So, these are the some of the more responses for the different bacteria, right. This is the typhi medium and that was the E. coli. So, you can see their sensitivity is coming different for the different kind of antibody. Okay, and here we have compared using the anti-E. coli antibodies. So, the first graph is basically for the E. coli detection, right, and these are the like 100 CFU and 1000 CFU and 2000 CFUs we have detected. This is again these are the selectivity basically. So, you can see when we are using the this kind of sensors. So, here the red graph is basically MOS2 antibody and the gold. So, you can see the graph is going very you can see their response is very high. So, then that is going straight, and then the black line is without the MOS2 or antibody. So, from here you can conclude like we are getting the better sensitivity as well as the without the covalent bonding chemistry. So, this is also it is a recent work, right, and then another kind of sensor same MOS2, but for the detection of the protein, right. So, we have detected the bovine protein. So, using the anti-bovine antibody. So, this we have published in the scientific report. So, I hope we have some more time. Sensing length is around 2 centimeter.
Is there any variation if we will increase the sensing length or decrease the sensing length?
Actually, only the thing is like sensing length you can increase or decrease. Only the thing is like if you have a coating gold coating facility in such a way, so that if you can coat it, but it won't have any impact on the sensitivity, right. So, sensitivity would be same, right, whether it is 1 centimeter or 2 centimeter, but in general, because in SPR the sensing length is not much, right, because SPR wave is not traveling longer distances, right, it is die out in very short distance, right. So, that is why the total length could be like your half a meter or something like that, the total length of your sensor, or maybe some 10 15 centimeter. So from the detector like spectrometer to the source, right? But the sensing where the gold is coated, and another thing is if you increase the sensing length, so you need a more antibody, and antibody is cost, yeah. No, there is no bending because it's a straight. This fiber is basically 600 micron fiber, right? It's not like 150 micron, right? It's a 600 micron fiber and 400 micron fiber. So that is what for the SPR people are using those fiber, right? So similarly, one can see from here, these are the transmission spectrum, right? For the again. So now I come to this D fiber SPR biosensor. So here what we have done, we have edged the optical fiber. So D is basically, as you know, right, it can burn. So you have to use all the kind of protective gadgets, then only one has to use. So we have used, these are the photograph of the D fiber, these are all the experimental results, right. So we have done all the experiments, right. And then the thing is, as compared to the normal SPR, like normal people are doing the SPR, this D fiber SPR is a more sensitive, right, because of this discontinuity in the edges, right. It basically it provide a better more enhancement of this more bi-components of the Ponting vector is crucial for the coupling of the plasmons, right. And if we do this kind of D, so they are coupling more efficiently, right. And these are the some of the coating and all those, so that I'm just going through just for the purpose of the their characterization, right. So here we have basically detected the CTC, they are the circulating tumor cells, right. So when there is some cancer or some tumor is starting the body, right. So at that release the circulating tumor cells, and they are traveling in the stream of your blood, right, and they can again go and they metastasis any part of the body. So the thing is like if it can be early detected, right, or maybe can be used for the screening purpose. So then people can know like yes, some kind of cells or tumor cells are there in the blood stream. So that can be, then it can be prevented. Like we have also then discussed with the oncologist in the PGI Chandigarh and all with our study, right. But the thing is their opinion is different because they are the doctors, so they told like we are doing the biopsy, and they are more comfortable the biopsy because under the microscopy they'll see whether the tumor is healthy or not healthy. So then, but of course we have the projects on this, so then we have demonstrated yes, this technique can detect, right. So then you can see like we have done this because this they are called the we have done HEP G2 cells. They are the basically liver cells, basically cancerous liver cells. So then those cells we have taken from Pune laboratory, and then we have used the antibody of this CTC. So only their concern is their main point is it going to be more costlier because of the you are using the antibody, and then it is also not that specific basically, right, because this antibody is basically attracting all other cells also, not only one particular, because there is a lot of different kind of cancers, right. So it can be a breast cancer or maybe some other kind of cancers, so they are not very specific, right. So aptamer technique is even more specific towards the to detect the cancer cells. So because they are aptamer people are developing for that particular kind of biomolecules, right. So you can see like this is we have tested and we have detected around 10 cells also and they are the all they are the spiked sample, right? Like we have spiked them in the yes, human serum, and then that is how we have detected them. So the future is like as I have mentioned, because I have also mentioned the futuristic, like future perspective. So you see, this sensor or this sensing platform, they can be more realistic and more useful if they can be integrated with the microfluidics, right? So using the microfluidic device, that you can, as you can see here, this is the glass substrate, gold film is made, and this is the micro channel. So from where your biomolecules is flowing, right, in a very small quantity and in a controlled environment. So then it can be made as a device kind of thing, so that it can be used for the such kind of purposes, right. So this is like one of the thing, like using the microfluidic chips with the surface plasmon resonance biosensor, it can be a more useful and more realistic. Okay. Photonics biosensor, if you talk of, so then now people are using the silicon photonics. Since silicon photonics, basically we are also working on the this micro ring resonators, right. So their dimension, it is looking a very big, but their dimension is of the order of the micrometer, right. This ring and all, so they are very good device, and then they can be made like this. So in one particular flow cell, the ring resonator is inside, and then one inlet and outlet, and then there is a detector. So this is a complete device, and then you have all those ring waveguide. So this is basically silicon photonics. For this, of course, this kind of to make or to fabricate such device, you need a very world class facility, that is called the clean room facility, to fabricate such kind of things, right. Then nowadays you have also, if you have heard about the meta surfaces, so they are also engineering structures, special engineering structures, which giving the special kind of functionalities, right. So they are called the this is our own work, but this is a simulating work, right, because we do not have the fabrication facility also in our laboratory. Now we are developing. I'll show you in the next slide. So these kind of, and you can see their dimension is order of the 150 nanometer, 110 nanometer, and they are the basically asymmetric structures, and because of the asymmetricity, they are giving these kind of phonoresonances, right. And then if you basically work on this portion, right, here you can put your biomolecule. So then there is just change in this resonance wavelength, and then you can do the sensing. So the thing is, one ring is like this, and then the whole sensing platform is up to this, right. So these kind of, these are the futuristics. So then I thought of to show the some futuristic kind of research, so that people can also focus on such kind of research. So how to do the on chip photonics basically, right. So that in that direction we have started some of the work in our lab. So now we are establishing the clean room and the micro and nano fabrication facility in CSIO. It's one of the unique facility we are establishing in the North India. Like in any IIT or any other institution, no such facility is existing, right, because it is dedicated for the glass substrate, right, and silicon substrate, because people are having some limited, you can say, not bigger, but some limited kind of facility, but for the semiconductor, like we are now we are class 1000 and class 10,000 both, right. So depending upon which substrate we are using, so then accordingly, because for the semiconductor chip we need to have a class 100 basically, right, and even if you go for the 30 nanometer technology, then people are using class 10, right. So but our purpose is to make the for the defense and strategic application, to make the beam combiner and to make the waveguides on the bigger substrate, right, at around about 6 inch 6 inch and 10 inches, right. So, that is very big platform. So, such kind of things we are targeting. So, as you can see large area basically, right. So, size is 10 nanometer to 10 micron feature size, right. So, it can be like used for this such kind of application like QPIC, quantum photonics integrated circuits for the quantum technology. So, basically you know like now our government of India and our honorable Prime Minister, they are very keen for this quantum technology, and they have also launched the National Quantum Mission. So, many institutions, they are part of that quantum mission, and then we are also working on to develop the entangled photon source, right. So, that to develop the entangled photon source or single photon source, you need to have such kind of facility to do the fabrication. Okay, and then that can also use for the quantum logic gates and processor making. Then CMOS integrated sensors. Some of our colleagues, they are working on the 6G components using the terahertz devices, right. They are developed this terahertz detector and modulator, right. Our major focus is basically the laboratories has developed the head-up display for the Air Force, right. So, that is our major this thing, right, footprint for the laboratory, and only one of the in India, only we are the people like in the India who's developed this for the fighter aircraft LCA, right. So, now this is the conventional HUD, but using this such facility, now the target is to make the waveguide HUDs, then reduce the size and their weight and all those things, right. So, this facility is very unique, which can cater the need of the many other institutions also, right. So, using that facility, we are also targeting to make the micro lens arrays, micro nanophotonics components, meta surfaces, quantum optics, sensing. So, these are the and you can see like so far even today, even in India, many our IIT like institutions through their startups, they are making spectrophotometer, right. So, spectrophotometer, but still the components of the spectrophotometer is imported. The grating, which is a very essential part of the photometer, spectrophotometer, it is not made in India. So, if such facility is there, then we can make those kind of gratings for the spectrometer, right. So, that also like that also was one of the good step, you can say the way forward in some other to make the some other devices, right. So, basic requirement is basically you have to build the clean room facility, micro and nano lithography tools. So, we have EBL, it is already like in process to come, electron beam lithography. Then we have etching tool, so that the pattern can be transferred to the actual device. Then deposition tool, right, if you wanted to deposit some other material also, right, and then characterization tool, of course, they are the very essential part of the process. So, these are the application of the silicon photonics devices like lab on chip, biosensor, quantum computation, neural network, artificial intelligence, quantum key distribution, 5G and future network, and data center and communication. So, these are the basically capability of the silicon photonics devices. These are the required simulation tools also, like the people those who are working in the like they do not have the experimental facility. So, they can do some good simulation for the silicon photonics. So, these are the very good platform like Photon Design, Synopsys, Lumerical, OptiWave. So, there are many tools, they are providing you a very good simulating platform, which can be later on realized in reality, right. So, then that can be your idea and design can be tested, right. This is the one of the example I have taken from this thing, like this is very recent, it is asymmetric Mach Zehnder interferometer biosensor. It is already available online, right. So, this is like a very most sensitive chip, right, base transducers, and that detect the change in the refractive index at the order of the 10⁻⁸ refractive index unit, right? And it also overcome the inherent sensitivity limits in other sensing components like ring resonator with no theoretical limit to functionalize the sensor area available. So yeah, it has a very low noise and integrated signal reference cancel out the noise from the environmental effects. So these are the like 8 arrays of the Mach-Zehnder interferometer. So this is basically some photonic integrated circuits I have taken. I think it is in Canada or somewhere they have developed, right? So it's a very good sensing device. So which can go as a chip for the sensing biosensing application. So with this, thank you. I summarize like I have I have just presented all this, right? And now I acknowledge my director and some of my colleagues. With this, thank you. I don't took now I will not take much time because I am in between you and your lunch.
I have a question.
Sure.
Yeah, you showed there was a slide on Salmonella typhi.
Yes, sir.
So after the bacterium gets attached to the
Surface.
so how do you detect it? What is the platform that is used to detect
Platform is optical fiber.
it? So what changes?
Change in wavelength. That I have shown, it's a change in wavelength.
I did not understand that from your slide.
Okay, so can I go back?
Yeah, if you can. You don't have slide numbers, otherwise I would have pointed you out to the slide number.
No problem. I remember. Yeah, here.
No. Salmonella typhi.
Typhimurium. Yeah, Salmonella typhimurium.
So you had one flow chart.
Yeah. This is the Salmonella typhimurium.
No, go back. Yeah. One more slide. One more.
Here?
One more.
Yeah.
One more.
This is the last.
One more. Yeah. So,
Huh.
so after the bacterium gets attached
Yeah.
at the last portion.
Yes.
So how do you detect it now? What changes that?
Yeah. So that is the thing is like because after this we have not shown the device basically.
The platform. Yeah.
Yeah, that is the basically interrogator, right? So which is reading the change, any change basically in that platform. So these are the kind of detection.
Yeah. So I can understand that there's a frequency shift.
Yeah. Change in the
But
frequency.
what is it the frequency shift due to mass or what?
No. Yeah, that is why it is changed because of the refractive index.
Okay, the refractive index is changing.
I have mentioned like this, all the optical fiber sensor they are based on the refractive index basically.
So only the refractive index changes.
Yes. Change in, because of the they are changing the refractive index because of the antibody and the antigen interaction.
Okay.
Yeah.
Thank you very much.
Thank you. So, any question from the audience?
This sensor life.
Yes.
Because what we generally find that there is a lot of variation in the sensors across, different domains. So, how do we test the efficacy of a particular sensor, and then because to avoid
in terms of their long life, like in terms of their
because the average life of a sensor is 10 to 15 years.
Yeah,
Depends. That's the average life.
Exactly.
But most of the labs which are using these sensors, they're not calibrating it. So calibration is one of the ways. So do we have some kind of device which can check whether the sensor is working well or not?
Actually, you see, if you talk of the physical sensor, for example, right? Like if you are using, let's say, for some structural health monitoring or some other things, right? So once let's say you have surface mounted or maybe you integrated some sensor in the bridge, for example, right? So the what people are doing, they are doing periodically monitoring, right? But in case of this biosensors, so they are the basically you have to use once you coated the antibody. So it is not the life of the sensor. Sensor life is good, but your biomolecules maybe they may not work after few hours, right? So after attaching you have to test it immediately. Maybe the sensor can be reused, right? You wash it. Again you can do all those chemical treatment and then again you can use it, right? So there's no problem with the sensor. But of course if you talk of whole platform, then you have to again redevelop it, right?
Any more questions from audience? Thank you, sir. Thank you so much for your enlightening session on optical fiber biosensors. Moving on, now I would like to request Professor Nidhi Sharma, ma'am, Dean Applied Science, to present a token of appreciation to Dr. Umesh Kumar Tiwari, sir. I would request Dr. Noor Zaman Khan to come forward and accept the token of appreciation from Nidhi Sharma, ma'am. I would invite Vanita ma'am and Sonal ma'am to join Nidhi ma'am. Thank you, everyone.